Hello and good evening to everyone, guys. I welcome you all to this wonderful channel by Unacademy NEET English. Well, my name is Kar Khurshid Alam and you can also call me KK sir. Well, enough about me. So tell me what's going on in your life. I believe everything is going good. Before we move ahead, I want quick confirmation that if you can see me clearly and hear me clearly, let me know in the chats. Let me know in the chats if you can see me clearly and hear me clearly. Let me know in the chats. Okay. All right, guys. I believe we are live now and super excited to start the today's session on Haloalkanes and Haloarenes. In today's session, we will discuss everything related to this chapter, so that no question can even dare to bother you in the NEET examinations. If you have not studied this chapter yet, be with me. We will kick off the session very nicely. But before starting this session, I would want you all to mark the attendance by smashing the like button and show some josh in the chats. Quickly. Mark the attendance by smashing the like button. Mark the attendance by smashing the like button and show some josh in the chats. Quickly. Show some josh in the chats. Come on. How is the josh? Let me know in the chats. How is the josh for today's session? Let me know in the chats quickly so that I can start today's session. Come on, guys. Come on. How is the josh? Yes, josh is very high. I think so. Come on. So without wasting time, let's get going. First question in this session will be nucleophilicity versus basicity. But before doing this, we must know what is meant by a nucleophile and what is meant by nucleophilicity. Similarly, what is a base and what is meant by basicity. Now have a look. Nucleophile, first of all, means species which can donate electrons to the electron deficient site, of the substrate. For example, if you have a substrate like this, where this Lg is the leaving group. Now, when you treat this with a nucleophile, say for example nucleophile 1, what will this nucleophile do? It will simply donate its electrons to the electron deficient site and here leaving group will leave. Now, listen carefully. Have a look. Now, let us suppose leaving group leaves and it results in the formation of this one plus Lg. Similarly, if we are having similar substrate but it reacts with another nucleophile, let us suppose Nu2 having a negative charge. Now this nucleophile will also donate its electrons to this carbon, electron deficient carbon, and here leaving group leaves. So the product becomes RCH2 and then Nu2 plus leaving group leaves with say electron. That means this is having a negative charge. Now listen carefully. Let us assume what? Let us assume that rate for this reaction is R1 and for this reaction it's R2. Let us assume that rate of first reaction is greater than rate of second reaction. That means this reaction rate is say greater as compared to the rate of this reaction. That clearly indicates that this nucleophile attacks this substrate easily, or we can say this nucleophile gives its electron to this say carbon or electron deficient carbon of this substrate more readily as compared to this. Therefore, if rate is this, therefore we can simply say nucleophile 1 having a negative charge is stronger nucleophile as compared to 2. So this is strength of nucleophile, or this is known as strength of nucleophile, or simply nucleophilicity order. So now have a look. Nucleophile is any species which can donate its electron to electron deficient species, but other than hydrogen. Electron deficient species or electron deficient site of the substrate, but other than hydrogen. Here, can I say this nucleophile is stronger nucleophile than this nucleophile because rate of this is greater than this. That means this nucleophilicity or the strength of nucleophile depends on rate of the reaction. Now, remember, as nucleophilicity depends on rate of the reaction, depends on the rate of a reaction. Hence we can say nucleophilicity is a kinetic property. As it depends on rate, hence it is a kinetic property. Now have a look. We assume that this rate is greater than this. After this assumption that rate is greater than R1 is greater than R2, after that we can say that Nu1 is stronger nucleophile than Nu2. That clearly indicates strength of nucleophile or nucleophilicity is rate dependent, and any species whose which is dependent on rate, like nucleophilicity, as it depends on rate, any species which depends on rate, we simply call that species is showing a property known as kinetic property. As nucleophilicity depends on rate, hence nucleophilicity is showing simply kinetic property. Now have a look. What actually nucleophilicity means? Nucleophilicity means strength of nucleophile, but can we say nucleophilicity is simply tendency of a nucleophile to form a covalent bond? Tendency of a nucleophile to form a covalent bond by donating its electron to the electron deficient site. So nucleophilicity simply means tendency of a nucleophile to donate its electron to electron deficient site and tendency to form a covalent bond with that. So its tendency is more as compared to this. That means this is stronger nucleophile as compared to this. So we can simply say that nucleophilicity is tendency. Nucleophilicity is a tendency of a nucleophile. Tendency of a nucleophile to form covalent bond with electron deficient site. To form covalent bond with electron deficient site of the substrate. But remember, other than hydrogen. So simply we say that this is stronger nucleophile as this, that clearly indicates that this nucleophile can form covalent bond, stronger covalent bond with this as compared to this. Or this nucleophile is having tendency to form covalent bond more strongly as compared to this one. So I hope this is clear to everyone that simply nucleophile is a species which can donate its electron to electron deficient site of the substrate other than hydrogen, and tendency of any nucleophile to donate its electron pair to electron deficient site of the substrate other than what we call hydrogen is known as its nucleophilicity or strength of nucleophile, and nucleophilicity is a kinetic property as it depends on rate. I hope this is clear to everyone. Let me know in the chats, is this clear to everyone till now? Let me know in the chats, is this clear to everyone till now? What is nucleophile and what is nucleophilicity? And third thing, that nucleophilicity is a kinetic property. Is this clear to everyone? Come on, come on, come on. Reply quickly by showing fire emojis. Come on, come on, come on, come on. As we don't have much time in today's session, so let me know in the chats quickly. Is this clear? Radha Krishna, clear sir. Other students, Sadab Bhatt, yes sir. Aditya Gopal, video is blur. Okay, video is blur. Okay, give me a second, give me a second, give me a second. Now, is this clear? Is this clear now? Is video clear now? Okay. Afnan Zahur, now tell me, is video clear now? Is this clear now? Is this clear? Yes, sir, clear. Okay. Okay. Okay, great. Now, next thing is, what is base actually? Now, have a look. To most acidic hydrogen, or base is a species, or base is a species which abstracts most acidic hydrogen of the substrate. So only difference, nucleophile donates electrons but to the electron deficient site other than hydrogen, and base donates its electrons to the most acidic hydrogen of the substrate. Now, for example, if you are having a species, say you are having an acid, let us suppose HA is an acid, and this is treated, this is the substrate, and this H is the most acidic hydrogen, and this is treated with, say for example, B1 having negative charge as a base. Now what will base do? Base will donate its electrons to this hydrogen, acidic hydrogen, and will simply abstract this hydrogen without electron. So it will result in the formation of A minus plus B1 and H. Now as this donates hydrogen, so this is acid, this is its conjugate base, but it abstracts, it accepts hydrogen as proton. So this is base and this is the conjugate acid of the base. This is base and this B1H is the conjugate acid of the base. Similarly, if I treat HA with another base, say for example B2 minus as base, then this base will abstract hydrogen from this and it will result in the formation of A minus plus B2H. So this B2H is another conjugate acid, but this is conjugate acid of this base. Now let us assume that B1H is more stable conjugate acid than B2H. Let us suppose this is the stability order. Let us assume this is the stability order. Now tell me, if this is more stable, suppose this is more stable as compared to this, can I say this will be formed easily as compared to this one. If this is formed more easily than this one, than B2H, that clearly indicates that this base abstracts H more easily as compared to this. So therefore, we can simply say that B1 minus is a stronger base than B2 minus. So this is the basicity order, or this is strength of basic order. So this is basicity order, or this is order of basic strength. I hope this is clear to everyone. Now tell me, then basicity order or basicity, that means strength of base, that depends on what? That depends on stability of conjugate acid. Remember, any species which depends on stability is a thermodynamic property. So we can simply say that basicity is a thermodynamic property. Is a thermodynamic property. As it depends on stability of conjugate acid. Stability of conjugate acid. In nutshell, any species which depends on stability is considered as a thermodynamic property, but any species which depends on rate is considered as kinetic property. Now, the question is, how can we define basicity then? So can I say basicity is, basicity means tendency of a base to form covalent bond with most acidic hydrogen of the substrate by donating its electrons. So nucleophilicity is tendency of a nucleophile to donate electron, but to form a covalent bond with electron deficient site other than hydrogen. But basicity is tendency of a base to donate its electrons to form a covalent bond with most acidic hydrogen of the substrate. So basicity is a thermodynamic property, and what we call nucleophilicity is a kinetic property. I hope this is clear to everyone. Is this clear till now? Let me know in the chats. Is this clear till now? Let me know in the chats. Okay. Sadaf But Ji sir. Okay, let me know in the chats. Is this clear till now? Clear? Is this clear? Bhavya Jali. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Nice, nice, nice. The quality limit is 480. It's still blur. Okay, your board is too blur. Okay, let me do something. First, give me a second. Give me a second. Give me a second. Give me a second. Now, how is the quality? How is the quality now? How is the quality now? How is the quality now? Now, perfect, sir. Is it perfect now? Let me know in the chats. Is it clear now? Same as before. No, I think it's clear now, because I can also see from my own mobile. It's fine now. I think it's fine now. Yes, clear. Okay. Now, let's move towards our first question, and that is nucleophilicity versus basicity now. And this is, say, our first question, that is nucleophilicity versus basicity. you have to remember 5 or 6 points regarding this. But the point number 1 is, have a look. If you have a nucleophile, let me show some examples so that you can understand what exactly it's written over here. Have a look. If you are having a nucleophile in which nucleophilic center, that means that atom which can donate electron is oxygen, and second one is H2O. That means in this case nucleophilic center is oxygen. In this case it's also oxygen. So can I say nucleophilic centers are same? Nucleophilic centers are same. But what is the difference between these two? What is the difference between these two? Difference is of H positive. So if this is base, this is its conjugate acid. Or if this is acid, this is its conjugate base. That means here I have given you an example where OH minus and H2O are conjugate acid base pairs and both are having similar nucleophilic center. And one is negatively charged, another is neutral. Remember, if one is negatively charged, another is neutral, both are conjugate acid base pairs and both are having similar nucleophilic center, then that nucleophile whose negative charge is more is stronger nucleophile. Now tell me, nucleophilicity is or basicity is directly proportional to magnitude of negative charge. Where magnitude of negative charge is more, it's 1, so I can write down 1 greater than 2. So this will become nucleophilicity order. But remember, for such types of nucleophiles, basicity order is also same as that of nucleophilicity. That means for such nucleophiles, nucleophilicity and basicity parallels with respect to each other. So can I say now, if nucleophilic centers are same and are conjugate acid base pairs, at that time nucleophile having more negative charge is stronger nucleophile than water. Similarly, another example, if I write NH2 having a negative charge and second one NH3, both are conjugate acid base pairs and the difference is of proton. We know conjugate acid base pairs differ by means of a proton. So here nucleophilic center is nitrogen, here also nucleophilic center is nitrogen. So both are having same nucleophilic center and are conjugate acid base pairs. One is negatively charged, another is a neutral species. Now tell me which one among them is having more negative charge. It's NH2 minus, so I will simply say NH2 minus is a stronger nucleophile than NH3. Now tell me, is first point clear to everyone? Is this point clear to everyone? Let me know in the chats quickly. Let me know in the chats. 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 Give me a second. Once again, I will throw a little bit. Give me a second, guys. Give me a second. Give me a second. Is till then you can let me know, is first point clear to everyone? Is first point clear to everyone? You can tell me till I simply adjust the camera. Now, is this clear? Is this clear now? Yes, I think now it's clear. Now it's clear. I think this is fine now. Let me know in the chats. Let me know in the chats. So good now. Okay, thank you. Now, so this was point number 1. Point number 2 is like this. Have a look. If you are having, let me show you one example in this. if you are having RO having a negative charge, second, if you are having OH having a negative charge, number third, if you are having a phenoxide ion like this, and you are having a carboxylate ion. Now have a look. Nucleophilic centers are same, oxygen, 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 oxygen. But remember, these are not what we call conjugate acid-base pairs. So if nucleophilic centers are same, but are not conjugate acid-base pairs, at that time, nucleophilicity or basicity parallels with respect to each other, and nucleophilicity or basicity, they are inversely proportional to stability of these species. So more stable the species, lesser will be its nucleophilicity or basicity. Now have a look. As this is alkoxide ion, R will donate its electron due to plus I, so its negative charge will increase. This H neither what we call donates electron nor withdraws electron. That means this HO or OH minus is more stable than RO minus. But as compared to OH minus, this O minus phenoxide ion, O minus of phenoxide ion shows resonance. That means this is stable because of resonance. This RCO minus also shows resonance. But in this case, resonance is equivalent. And in this case, resonance is non-equivalent. So resonance is equivalent means resonance is more in 4. That means RCO minus. Hence, 4 is most stable. So let me write down the stability order first. So stability order of these species will be RCO O negative. After that, it will be phenoxide ion. After that, it is hydroxide ion, phenoxide ion. Then after that, it's hydroxide ion. And lastly, it is alkoxide ion. I mean, say this is stability order. So can I say, therefore, nucleophilicity or basicity, nucleophilicity or basicity will be simply reverse to that of stability. I mean, say inverse to that of this. That means RO minus will be a stronger nucleophile or a stronger base than OH minus, which in turn is stronger than phenoxide ion, which in turn is more stronger base or a nucleophile than RCOO negative. I hope this is clear to everyone. Now let me know, is point number second clear to everyone? Is point number second clear to everyone? Let me know in the chats. Is point number second clear to everyone? Is point number second clear to everyone? So that we can move towards point number third. Come on guys, you can let me know in the chats quickly. Yes sir, clear sir. Great, great, great. Everyone please, everyone please. Yes, 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 yes. Be focused in today's session. Everyone, everything will be discussed over here. But be very much focused in today's session. Come on, have a look. So next point is, say for example, if you are having a nucleophiles or bases like this, CH3 minus, then you have NH2 minus, then you have OH minus, then you have F minus. Now have a look. Can I say negative charge or the nucleophilic center is carbon, nitrogen, oxygen and fluorine. Now have a look. Carbon, nitrogen, oxygen, fluorine, they belong to the same period. When we move along a period, their electronegativity increases. And if electronegativity increases, their negative charge of electrons will be tightly bound, will be tightly held. So it will be tightly held, it will be loosely held. So which can act as a good nucleophile or a base, which can donate its electrons easily, and which can donate its electrons easily, whose electrons are loosely held. That means if elements, if nucleophiles or bases belong to the same period, then at that time nucleophilicity or basicity, they are inversely proportional to electronegativity. So can I say here it will be CH3 minus, then NH2 minus, then OH minus, then I mean to say F minus, which will be our nucleophilicity as well as basicity order. So this will be our nucleophilicity versus basicity order, or nucleophilicity as well as basicity order. So in point number 1, nucleophilicity parallels basicity. In point number 2, nucleophilicity parallels basicity. And in this point, nucleophilicity parallels basicity as well. Now have a look. Another point is point number 4. Now have a look. We can understand this with the help of example first. Now, I will write down over here. Say for example, if you are having F minus, you are having Cl minus, you are having Br minus, and you are having I minus. Please listen carefully. Now, these belong to the same group, F, Cl, Br, and I. In general, we know size increases on moving from top to bottom. What we will do, in general, we say that on moving from top to bottom, size increases. And if size increases, their nucleophilicity also increases. So in general, nucleophilicity order is I minus is a stronger nucleophile than Br minus. Br minus is stronger nucleophile than Cl minus, and Cl minus is stronger nucleophile than F minus in turn. So this will be nucleophilicity order, and nucleophilicity will be directly proportional to size, but if elements belong or nucleophiles or bases belong to the same group, and this is in general. This is in general most of the times. If solvent is not given, then you have to write down this order. Similarly, you will write F minus greater than Cl minus greater than Br minus greater than I minus, and this will be the basicity order. This will be the basicity order if bases belong to the same group. But this nucleophilicity order is only if what we call solvent is not given. In actual sense, it is nucleophilicity is, remember, nucleophilicity is solvent dependent. What does that mean? That means if solvent is changed, nucleophilicity will change. Now, have a look. First of all, in polar protic solvent, for example, if we talk about water. Now, for example, we are talking about polar protic solvent, and that example is water. Now, have a look. We are having F minus, Cl minus, Br minus, and I minus. Now, tell me, whose size is larger and whose size is smaller? You know that because F, Cl, Br, I belong to the same group, and on moving from F to I, size increases. That means this is smaller in size and this is largest in size. Now, we know all are having negative charges, and we know negative volume charge density. Negative volume charge density is equal to magnitude of negative charge divided by size. Now, have a look. As all are having -1 charge, that means magnitude of negative charge is same. As magnitude of negative charge is same, can I say negative volume charge density is inversely proportional to size? Why? Because all are having same magnitude. Now, have a look. Any species whose size is less is having more negative volume charge density. So, can I say this will be having more negative volume charge density? Hence, as we know, water is a bipolar species. It's a dipole. So, the positive part of water will surround this. I mean, say hydration will take place or solvation will take place. Let us suppose this is solvation. Suppose this is solvation. So, can I say here solvation will be more? Why? Because negative charge holding capacity, negative charge volume charge density of F minus is highest in among Cl minus, Br minus, and I minus. Why? Because its size is smaller. If negative volume charge density is more, negative volume charge density is more H positive will attract or surround this F minus. Now, as compared to F minus, Cl minus will be surrounded by less number of solvent molecules. But as compared to Cl minus, Br minus will be surrounded by less number of, water molecules or solvent molecules, because more the negative volume charge density, more will be the attraction with H positive of the solvent, or what we call positive part of the solvent. Similarly, I minus is having lowest volume charge density, hence its attraction with water molecules, with solvent molecules will be less. So, can I say this is most solvated and this is less solvated? Now, tell me. If more solvent molecules are surrounding this as compared to I minus, so can I say I minus is what we call less hindered as, less surrounded as compared to F minus. So if it is less surrounded, it will attract electron deficient site. It can donate its electron pair to electrons to electron deficient site of the substrate more easily as compared to Br minus. Br minus can donate its electrons more easily as compared to Cl minus, and Cl minus can donate its electrons easily than F minus. So can I say nucleophilicity order will be like this: F minus, Cl minus, Br minus, and highest nucleophilic site will be, stronger nucleophile will be I minus. So this is nucleophilicity order. This is nucleophilicity order in polar protic solvents. Because more negative, lesser size, more negative volume charge density, more negative volume charge density, more solvation, lesser will be the nucleophilicity. So I minus is stronger nucleophile than Br minus, than Cl minus, than F minus. That means same trend as that of when solvent is not given. When solvent is not given, general trend is this. And if solvent is not given, we basically take water as solvent. That's why these two, orders are one and the same. I hope this is clear. Now, after that, if I take solvent like polar aprotic solvent, if we take solvents like polar aprotic solvents. Now, these are polar, but these are not having any, they cannot donate proton. Let me show you who can donate proton basically. Whenever hydrogen is attached to more electronegative elements like fluorine, chlorine, bromine, iodine, oxygen, nitrogen, if they is attached to sp hybridized carbon, etc., more electronegative elements. So this hydrogen can be easily removed as H positive. Now have a look. If you have water, so can you say this is polar protic solvent? If you have alcohol, can you say this is polar as well as it can donate proton? That means polar protic solvent. Similarly, if you are having RCOOH, so can I say this is, polar as well as it can donate proton. So these are polar protic solvents. But if I write like this, CH3, C double bond O, CH3, acetone. Here carbon is having slight positive charge and oxygen slight negative charge. That means this is polar. But where can I say hydrogen is not attached to sp hybridized carbon or more electronegative element? That means hydrogen is there, but it cannot donate proton. So this is polar aprotic solvent. Acetone is a polar aprotic solvent. Dimethyl ketone, propanone, whatever you want to name this. This is either propanone, dimethyl ketone, acetone. Okay. Similarly, if I write like this, this is known as dimethyl sulfoxide, known as DMSO. Dimethyl sulfoxide, DMSO. This is also polar, but without, proton. It cannot donate proton. That's why polar aprotic solvent. Similarly, if I write like this, this is formamide. If I remove hydrogens by methyl, so this is known as dimethyl formamide. This is known as dimethyl formamide, DMF. So these are what we call polar aprotic solvents. Similarly, if you write like this, P double bond O, then NCH3, CH3, NCH3, CH3, similarly NCH3, CH3, this is known as hexamethyl phosphoramide, HMPA, hexamethyl phosphoramide. This is also what we call polar, but it cannot donate proton because proton is not attached to more electronegative element. Hence, these are few examples of polar aprotic solvents. Now, have a look. If I take F minus, Cl minus, Br minus, and I minus. Remember, in polar aprotic solvents, these are not solvated. These are not solvated. Why? The question is why? Why they are not solvated? Because solvation means attraction of positive part of a solvent and between this negative ion and positive part of a solvent, so that positive part of solvent can come and surround these negatively charged ions. But in these cases, positive part cannot surround these negatively charged ions. Have a look. If this positive part is, trying to, surround this, there will be repulsion because of these bulky groups. Have a look. Have a look. These are bulky groups. So electron cloud of these bulky groups will repel electron cloud of F minus. That's why this cannot surround, F minus. Similarly, if this C positive is attracted towards, F minus, but the C positive is also having CH3 closer to it. That means bulky groups are there, so there will be repulsion. In nutshell, negatively charged ions or anions, they are not solvated in polar aprotic solvent. Similarly, you can have a look over here. These are the bulky groups. Similarly, this carbon positive is having this bulky group. So there will be repulsion between bulky groups of solvents attached to positive part of the solvent, bulky groups attached to positive part of the solvent, and negatively charged ions. That means these are not solvated. When they are not solvated, now which will attack to the electron deficient site of the substrate? We know mobility of ions is inversely proportional to size. Smaller the size, more mobile will be that ion. Hence, in polar solvents, as these are a polar aprotic solvent, these are not solvated. Therefore, nucleophilicity order will be. Nucleophilicity order will be. Nucleophilicity order will be simply F minus greater than Cl minus greater than Br minus greater than I minus. Now have a look. This order has been changed. Have a look. In this, I minus was a stronger nucleophile, but in this F minus is a stronger nucleophile. That's why the nucleophilicity is basically solvent dependent. But if solvent is not given, take water as solvent and write down the answer of a polar protic solvent. I hope this is clear to everyone. Now let me know in the chats, is this clear to everyone till now? Is this clear to everyone till now? Come on beta, let me know in the chats, is this clear to everyone till now? Come on. Let me know in the chats, is this clear till now? Everyone quickly, let me know in the chats, quick. Okay. If it is clear, drop few fire emojis as well. Now, next point is, another point is like this. If nucleophilic centers are same, now have a look, example. If nucleophilic centers are same, but these are attached to different alkyl groups. Nucleophilic center is O, it's attached to ethyl. Now, nucleophilic center is O, but it's attached to this isopropyl group. After that, nucleophilic center is same. That means once again it is O, having a negative charge. But now it is attached to tertiary butyl group. Now, what will happen? Remember, at that time, nucleophilicity order depends on size like this. If you are having nucleophilic center same, but size of alkyl group increases, that means on moving down the group, size increases. So, if size increases, when this nucleophile attacks the electron deficient site, there will be repulsion, because more the bulkier group, more will be the, steric repulsion. Hence, nucleophilicity is inversely proportional to size. That means nucleophilicity order for this question will be, it will be 1, 2 and 3. Why? Because as size increases, steric repulsion increases. Steric repulsion increases, nucleophilic character decreases. Hence, nucleophilic order will be this, but nucleophilicity order is actually based on, this order is based on steric repulsion. Based on steric repulsion. Based on steric repulsion. Now, what about basicity order? Basicity order is not dependent on steric repulsion. Hence, we simply have a look. We will simply see whose oxygen is more electron rich. This ethyl will donate its electron and its oxygen's electron density will be increased. But this alkyl will donate more electron, as this is having more what we call plus I effect. Similarly, this is having stronger plus I effect. It will increase electron density of the oxygen more. So, more the electron density of the oxygen, more will be the donation of its electrons. Hence, answer will be 3, 2 and 1. I hope this is clear. So, Nucleophilicity is based on steric repulsion, but basicity is not dependent on steric repulsion. Last point is like this. Have a look, have a look. If you are having a nucleophilic center, say for example oxygen, and after that nucleophilic center is once again an oxygen, but this is a nucleophilic center, and to its adjacent position, that means at alpha position, another heteroatom is there which is having lone pair of electron. Now have a look. Here this is the nucleophilic center, but to this hydrogen is attached, that means it is not having any lone pair. Now what will happen over here? Here basically because of repulsion, remember, actually nucleophile when donates electrons, it is actually its highest occupied molecular orbital. Remember forever. Nucleophile basically donates its electrons, and that orbital which donates its electrons is actually highest occupied molecular orbital, that means HOMO. And it donates to electron deficient site of the substrate, and that part of the substrate which accepts electrons, basically its orbital is LUMO, lowest unoccupied molecular orbital. So this is of nucleophile, this is of electrophile. I mean say that part of the substrate, that site of the substrate which attracts, I mean say which accepts electrons. Now have a look. As we are talking about nucleophiles, I will rub up this LUMO. Now nucleophilic site, remember here negative charge and electrons, that means at adjacent position charges are same, so there will be more repulsion as compared to this. More repulsion increases basically energy of HOMO. So when it increases energy of HOMO, that means it becomes less stable or it becomes more reactive. More reactive means more stronger nucleophile. Hence 2, that means hydroperoxide ion is a stronger nucleophile as compared to OH minus because of repulsions. And repulsion takes place because alpha atom is having lone pair. That's why this is known as alpha effect. Similarly, another example. If you are having ammonia, here nitrogen is the nucleophilic site, but if you take an example of hydrazine, say for example this is the nucleophilic site, then this is alpha, and if this is the nucleophilic site, then this is alpha. In nutshell, at alpha position there is an atom containing lone pair of electrons, so there will be repulsions. More repulsions increases energy. Energy is increased, stability will decreases, that means it becomes more reactive. More reactive means stronger nucleophile. Hence hydrazine is a stronger nucleophile as compared to ammonia, and the reason is repulsions taking place at say alpha position. So that's why this is known as alpha effect. So this was all about nucleophilicity versus basicity. I hope this is clear till now. Now next question. SN reactions means substitution nucleophilic reactions, or we can simply write down NSR, nucleophilic substitution reactions. Now we are having few types of these: SN1, SN2, we are having SNI, we are having NGP, but these two we are not going to discuss SNI and NGP in NEET. Now what is this? This is SNAR, nucleophilic substitution aromatic or aromatic nucleophilic substitution reactions, and these will be taken place generally in aryl halides. So first of all, we will be discussing SN1, after that SN2. Now have a look. SN1, full form of SN1 is simply substitution, nucleophilic, unimolecular reaction. Now have a look and listen carefully what actually SN1 reactions are. Now first of all, SN1 reactions are those reactions for which rate is directly proportional to molar concentration of the substrate. Now this is point number 1. So if I remove this proportionality term, so can I write proportional constant known as rate constant into molar concentration of the substrate? So this is rate law equation. Now it is clear from these 2 points that it's clear from this point that it is unimolecular. So SN1 reaction is a unimolecular reaction, and it is clear from this that it is first order reaction, or it follows first order kinetics. So it's a first order reaction. After that, remember, SN1 reaction is a multi-step reaction. It is a multi-step reaction. It's a multi-step reaction. Please try to understand. It's a multi-step reaction. And step 1 is always ionization step. Is ionization step or formation of carbocation. Ionization step or formation of carbocation, and is the slowest step of the reaction. Slowest step of the reaction. And hence, and is the slowest step, and hence RDS of the reaction. It's the slowest step, and hence it is what we call the rate determining step of the reaction. Have a look. For example, if we are having a substrate, let us suppose alkyl halide, tertiary butyl halide. Suppose we are having this as the substrate. Now, first of all, what will happen? Polar protic solvents. For example, water. Now, polar protic solvents have high dielectric constant value. What is meant by dielectric constant value? That means these solvents have highest tendency to simply separate these, ions apart. Now, have a look. Now, what will happen? It will help in breaking of this EX bond, and both these electrons will be taken up by X minus. So, here ionization will take place, or it will result in the formation of a carbocation. So, first of all, carbocation is formed, and then leaving group will leave with electrons. Now, this is step number 1. After that, you have to do rearrangement, because as carbocation is formed, rearrangement can take place. So, you have to do rearrangement if possible. But we know here there will be no rearrangement in this case. So, that's why step second will be simply attack of nucleophile on carbocation. Attack of nucleophile on carbocation. Say, for example, we are having a carbocation. In this reaction, it's like this. Now, suppose we are having OH minus as the nucleophile. I mean, say negatively charged species is acting as nucleophile. Now, what will happen? This negative charge, will donate its electron to electron deficient side and form a bond. And this is a very fast reaction. That means it is rate independent step. This was slowest step. That means this is rate determining step, and this is rate independent step. So, the product formation will be like this. Sometimes what will happen? Have a look. Sometimes what will happen? Instead of this negatively charged nucleophile, solvent will act as a nucleophile. Have a look. Solvent was water. That water will act, solvent will act now as a nucleophile. But you have to remember, when nucleophile is neutral, when it attacks on this, it will acquire a positive charge, because neutral species donates electron, acquires a positive charge. Finally, it will lose H positive. And when it loses H positive, so neutral nucleophiles always lose H positive and result in the formation of the product. Now, have a look. Now, this reaction in which nucleophile is a solvent, or solvent acts as a nucleophile, is known as solvolysis. What is that reaction known as? Solvolysis. Let me write down over here. Reaction in which solvent acts as a nucleophile. Solvent acts as a nucleophile is called solvolysis. And if water acts as a solvent, then it is hydrolysis. If alcohol acts as a solvent, then it can be alcoholysis. In nutshell, it is solvolysis. So, can I say, hence we can simply say, SN1 reaction can be solvolysis. It can be solvolysis. Why? Because here solvent can act as a nucleophile. Now, after that, you have to remember this point. That rate of, or simply we will write down like this, as intermediate of this reaction is carbocation, hence rearrangements can be possible. Now have a look. We are having now factors affecting say SN1 reaction. First factor is simply substrate structure. For example, if you are having CH3 CH2X, say 1 degree alkyl halide, you are having 2 degree alkyl halide like this, and you are having 3 degree alkyl halide like this. Listen carefully. What you have to do is just remove leaving group. Just remove leaving group and result in the formation of and forms what we call a carbocation. Remove leaving group and forms carbocation. Remove leaving group and forms carbocation. Remove leaving group and forms carbocation. Now have a look. When you remove leaving group and forms a carbocation, now have a look, without rearrangement. Now in rate determining step form a carbocation, but don't do rearrangement over here. Have a look. This carbocation, stability of carbocation depends on strain, aromaticity, back bonding, resonance, hyperconjugation and inductive effect. But strain means there should be the cyclic structure. As this structure is not cyclic, so we cannot answer this stability with the help of strain. Similarly, as it is not cyclic, we cannot explain their stability with the help of aromaticity. Similarly, carbocation is not attached to that atom which contains any lone pair of electron, so there is not the possibility of back bonding over here. Similarly, neither there are any conditions for resonance. Now, these can be explained either by hyperconjugation or inductive effect. But as hyperconjugation comes first in order as compared to inductive effect, we will simply look towards their alpha hydrogens. This is having 3 alpha hydrogens. This is having 6 alpha hydrogens, and this is having alpha, alpha, alpha. 3 hydrogens, 3 hydrogens, 3 hydrogens. That means 9 alpha hydrogens. So can I say more the number of alpha hydrogens, more will be the stability. Hence, this is more stable than this, than this. And remember, rate of SN1 reaction is directly proportional to stability of carbocation formed in RDS. Formed in RDS. That means substrate which forms most stable carbocation can show more easily SN1 reaction. So this substrate forms most stable carbocation. So what will be the order of SN1 reaction over here? Can I say it is 3, 2 and 1. So this will be the order, or this will be the rate of SN1 order. I hope this is clear. So rate depends on the structure of the substrate. That's why first application or factor is substrate structure. Now after that, point number second is effect of leaving group. Have a look, have a look. If you're having Ri, that means this is the substrate. RBr, this is the substrate, and then RCl, this is the substrate. RF is the substrate. Now tell me, can I say R in all these, R F, RCl, RBr, Ri, R is same. What is the difference between these? The difference is only of halogens or the leaving groups. So this substrate is having I as a leaving group, I minus, Br minus, Cl minus, F minus. That means now what we call rate depends on what we call leaving group ability. That's why we must know this, that rate of SN1, remember, is directly proportional to leaving ability of the group. Leaving ability of the group. Rate is directly proportional to leaving ability of the group. Remember this always. This is most important point, that rate is directly proportional to leaving ability of the group. But how can we say the leaving ability? Let me first of all rub this one. Let me first rub this. Now, have a look. Remember, leaving ability is actually directly proportional to stability of base. That's why stability of the base. That's why another formula can be R SN1. That means rate of SN1 can be directly proportional to stability of base. Or you can simply say R SN1 is inversely proportional to, basicity. That means weaker the base, that will be a stable base. Weaker the base is stable, and that's a good leaving group. And if that is good leaving group, rate is directly proportional to that at that time. Or you can simply say rate of SN1 is directly proportional to acidic character of conjugate acid of base. Directly proportional to acidic character of conjugate acid of base. Have a look. If I write Ri, what is the leaving group? I minus. If I write RBr, leaving group of this is Br minus. Have a look and try to understand. If I write RCl, leaving group is Cl minus. If I write RF, leaving group at that time is F minus. So, what we will do, we have to see which of the following is a good leaving group. We will simply have, say either we will simply use this formula, or this formula. Suppose I want to say I will use this formula. What is the conjugate acid of this? Its conjugate acid is Hi. What is the conjugate acid of this? Give proton to this, that means it is HBr. What is the conjugate acid of this? That is HCl. What is the conjugate acid of this? That is HF. And remember, if I write acidic character, we know this Hi is having more, say bond length. That means it's easier to break this, and to this Hi will easily donate H positive. That means this is stronger acid as compared to HBr. HBr is stronger acid as compared to HCl. HCl is stronger acid as compared to HF. Now tell me, this is an conjugate acid of this base. So we know acid and its conjugate base, or base and its conjugate acid, they are always opposite in nature. That means if this is stronger, this is weaker. If this is stronger, this is weaker. If this is weaker, this is stronger. Now tell me. If I have to see which of the following is, say a good leaving group, or which shows SN1 faster. So believe me, remember that if acid is stronger acid, or stronger conjugate acid of base, at that time that's a good leaving group. So I minus, Br minus, Cl minus, F minus, this is the leaving group ability order. This is leaving group ability order. So leaving group ability order, we have to calculate leaving group ability order. It depends, it is directly proportional to this. So this is the order, so this will be the leaving group ability order. So therefore, rate of SN1 will be Ri shows faster SN1 as compared to RBr, as compared to RCl, as compared to RF. So this will be the rate of SN1. This will be the order for rate of SN1. I hope this is clear. So whenever you have to find out rate of SN1, first of all, simply use leaving ability. You have to simply find out leaving ability, leaving group ability order. But leaving group ability order can be calculated with the help of this or this or this. I have used this formula right now. Now, let me know in the chats, is this clear? Is this clear? Let me know in the chats clearly. Let me know in the chats, is this clear? Quick. Let me know in the chats, is this clear till now? Any doubt? Any doubt? Clear? Let me know in the chats, guys. Let me know, as we are having very less time. Shabash. Let me know. Is this clear? Clear. Maria, Radhakrishnan, yes, clear. Okay. Other, super clear, sir. Good. Now, have a look. Now, another is, it is effect of solvent. Remember, rate of SN1 is directly proportional to dielectric constant value of the solvent. Why? Dielectric constant value of the solvent. Why is it so? Because more dielectric constant value of the solvent. Now have a look. Value of the solvent. Dielectric constant means ability, tendency, capability to separate carbon and X, to separate positive and negative ions. That means its ability to ionize CX bond. Now tell me, as the solvent whose dielectric constant is more, that means its ability to ionize CX bond will be more, and whose ability to ionize CX bond will be more is showing more SN1 reaction. But remember, generally polar protic solvents like water, alcohol, etc. favor SN1 reaction because they have high dielectric constant value. High dielectric constant value. So the solvent whose dielectric constant value is more favors SN1, or at that time rate of SN1 will be more, and those solvents are polar protic solvents like water, like alcohol. I hope this is clear till now. Now after that, another factor is presence of pi bond at alpha position with respect to leaving group. Have a look. If we are having vinyl halide, have a look. Similarly, if we are having aryl halide, if we are having vinyl halide or aryl halide, so X is the leaving group, so this is the alpha, so this is having pi bond at alpha position. Now what will happen? We know because of this there will be resonance. Similarly, there will be resonance. Now, after forming all the resonating structures, we can form their hybrid. So let me write down directly the hybrid. So it will be CH2 single bond, and this will be the partial double bond, and after that this will be the partial double bond. So this will be sometimes neutral, sometimes positively charged, sometimes neutral, sometimes negatively charged, but you have to write down all the resonating structures first. After that you will write down the hybrid. Similarly, its hybrid will be like this. So there will be partial double bond. Similarly, there will be a partial double bond. Now have a look. Now tell me, can I say when pi bond is present at alpha position, CX bond, that means bond of carbon and the leaving group, shows partial double bond character. When it shows partial double bond character, it's partial double bond character. That means partial double bond character means bond becomes stronger. Bond is stronger. So CX bond becomes strong due to partial double bond character as a result of resonance. As this bond is strong, so this is difficult to break. And if it is difficult to break, we simply say if pi bond is present at alpha position with respect to leaving group, at that time rate of SN1 is simply decreased. At that time rate of SN1 will be decreased. When? If pi bond is present at alpha position with respect to leaving group. So can I say vinyl halide and aryl halides, they are not good substrates for what we call SN1, or they will not show SN1 reaction at all because they cannot break their CX bond. Because for SN1 we have to break CX bond, we have to ionize we have to form carbocation, but here carbocation will not be formed as this bond is difficult to break due to partial double bond character as a result of resonance. So we simply says that this at that point of time when pi bond is present at alpha position with respect to leaving group, at that time rate of SN1 will be decreased. After that, what will happen? But before that, let me know in the chats, is this clear? Why vinyl halides and aryl halides do not undergo SN1 reaction? Let me know in the chats, is this clear? Let me know in the chats, but please quickly, let me know in the chats. Is this clear? Let me know in the chats. I'm waiting for your reply. Come on. We have to show that we can complete this chapter with concepts clear. Come on. Okay. Now after that, this is another, if you are having pi bond. Now, but this pi bond will be present now at beta position with respect to leaving group. Though this is alpha, this is beta. Say for example, allyl halide. Similarly, we are having benzyl halide. Say for example, benzyl halide. This is benzyl halide. This is alpha and this is beta. Pi bond is now present at beta position. So there will be no resonance. When there will be no resonance, so we can simply ionize this CX bond. But after ionization, it will result in the formation of, have a look. After ionization, it will result in the formation of a carbocation. And this carbocation is stabilized. This carbocation is stabilized because of resonance. And after that, you will see in hybrid that positive charge is dispersed. So more the dispersion of charge, more will be the stability. Similarly, here, carbocation is formed, which is resonance stabilized. So, can we say allyl halides and benzyl halides prefer SN1 reaction because they form carbocations which are stabilized because of resonance. So whenever you have whenever you have pi bond at beta position with respect to leaving group, at that time rate of SN1 is increased. That means such conditions favor actually SN1 reaction. After that, next condition is presence of heteroatom containing at alpha position with respect to leaving group. Have a look. If I write like this, this is what we call a leaving group. This is the leaving group. This is alpha, and to this alpha heteroatom is attached containing lone pair of electron. What will happen? Have a look. This CX bond will break. When CX bond breaks, it will result in the formation of a carbocation. But this carbocation is highly stable. Why this is highly stable? Because this carbocation is having empty orbital and its neighbor is having lone pair of electron. So there will be back bonding. So this is highly stable carbocation. Have a look. So carbocation is stabilized because of back bonding. So as carbocation is stable because of back bonding, therefore such conditions favor SN1. At that time SN1 will be increased. I hope this is clear to you. So whenever you are having a substrate in which there is heteroatom attached to alpha carbon with respect to leaving group, remember SN1 reaction will occur readily at that time because of formation of back bonding stabilized carbocation. After that, presence of electron withdrawing group. What will happen? Have a look. If you are having CH3, CH2, if you are having like this, if you are having CH3C, CH3, CH3 and X, and it undergoes, let us suppose, SN1 reaction. Suppose it undergoes SN1 reaction, it will result in the formation of a carbocation. And leaving group leaves. Suppose rate of this reaction is R1. Now, what will happen if I write like this? CH2, CH2, and here it is CH2. And after that, I will write down electron withdrawing group. Say for example NO2 instead of H. What will happen to this? Now have a look. When this undergoes, I mean to say formation of carbocation or SN1 reaction, these NO2 groups, these electron withdrawing groups, they destabilize, they simply destabilize the carbocation. They destabilize the carbocation by electron withdrawing. So if this is R2, can I say R1 is greater than R2? So R1 is greater than R2. That clearly indicates whenever electron withdrawing group is present in the substrate, at that time rate of SN1 is decreased. At that time rate of SN1 is decreased. Why? Because such groups, such electron withdrawing groups destabilize the carbocation, and we know rate of SN1 is directly proportional to stability of carbocation. If carbocation is not stable, rate of SN1 will decrease. After that, next point is like this. Presence of leaving group at bridgehead position. Now have a look. We know bridgehead position means a position which are basically common. So end common positions, these positions between two rings, end common position between two rings in a bicyclic compound is bridgehead position. So if I attach a leaving group over here, for SN1, we have to form, for SN1, we have to break this CX bond and we have to form this. I mean to say carbocation. But this carbocation, that means this bridgehead position. By doing so, bridgehead position becomes sp2 hybridized. Bridgehead position becomes sp2 hybridized. And hence violates Brett's rule. Because what is Brett's rule? Brett's rule says, let me write down over here. Brett's rule says bridgehead position can never be planar up to 8-membered rings. So if bridgehead position cannot be planar, cannot be sp2 hybridized according to Brett's rule up to 8-membered rings, so we cannot form positive charge at bridgehead position as it is highly unstable. Because we cannot form this, that means it is highly unstable. Hence, such condition simply does not favor SN1. That means SN1 cannot occur at that time. So I simply write down that this condition disfavors. It does not favor, it disfavors SN1. So such compounds do not show SN1 reaction in which this leaving group is attached to what we call bridgehead position. After that, next point is presence of ionic salts like AgNO3 and Lewis acids. In this AgNO3, Ag positive is there and that will also act as a Lewis acid. Have a look. If you are having alkyl halide and we simply this alkyl halide simply undergoes SN1 reaction and say for example this SN1 reaction takes place in presence of Lewis acid, say for example Ag positive from AgNO3 or any other Lewis acid, say for example BF3. What will happen? This lone pair basically forms a bond with this one and as this becomes X positive, so it will be easily removed. Similarly over here. So we simply say that such conditions favor SN1. Such conditions favor SN1. So here also SN1 will be favored. So in presence of, say Lewis acids, SN1 rate is simply enhanced. So this reaction is rate of this reaction is increased due to presence of such groups, because in presence of such groups this X or CX bond is cleaved easily, because by donating electron this X will donate electron and it will acquire a positive charge. More positive it will acquire, more easily it will break this CX bond. I hope this is clear till now. After that there are a few questions. Now first is complete the following. As this is an alkyl halide, here water is there, so remember you have to write down this reaction via SN1. So first of all, what will you do? You will form a carbocation like this, CH3, C, CH3, CH3 and then CH2 with a positive charge. After that, in this you will first form more stable carbocation by simply shifting this one. So here at adjacent positions, that means at 1,2 position, we will shift methyl carbanion. So this is 1,2 methyl carbanion shift. Why carbanion? Because methyl is shifted with electron, that means with negative charge and carbon. So methyl carbanion shift and it will result in the formation of this carbocation. CH3, CH2, CH3. Why this shift has been taken place? Because here now it is stabilized by 8 alpha hydrogens. Here it was only stabilized due to inductive effect because there were no alpha hydrogens. So this is more stable carbocation. After that, water will act as a nucleophile, that means this is solvolysis or hydrolysis. Water will attack on this, water will attack on this, and as we know water is a neutral nucleophile, it finally loses H positive and it will result in the formation of CH3, CH3, here it will be OH and this will be CH2, CH3. I hope this is clear to you because here rearrangement takes place. Similarly, this will be broken first and it will result in the formation of, but this carbocation will not undergo rearrangement as this is stable carbocation, and finally water, that means, will act as a nucleophile, hydrolysis will take place, and by doing so water will attack this carbocation, finally will lose H positive, and this will be the product of the reaction. So you have to look that intermediate carbocation is, you have to look whether that carbocation undergoes rearrangement or not. Here rearrangement takes place, so you have to form first more stable carbocation, after that nucleophile will attack to that carbocation. Here there is no, what we call a rearrangement, then it will form. Now here, first of all, it will form this carbocation, and you know, whenever carbocation is part of four-membered ring, you have to simply contract that ring, known as ring contraction. So 1, 2, 3, this bond will be broken and it will result in the formation of carbocation like this, or we can write down cyclopropyl methyl carbocation in this fashion. Finally, this is the most stable carbocation. Why? Because here this is not actual structure, this is one of the structures. When you draw all the structures, this is stable because of dancing resonance as compared to this, or this is stable because of bent hyperconjugation, or this is stable because of what we call sigma resonance. So after that water will attack and it will result in the formation of alcohol. But as I know that we have already done that rearrangements and all that, so you can simply solve these questions as well. Now these are the few questions for your home assignment. You have to try out these. Now have a look. If this CX bond is broken, have a look, I will show you this one. If this CX bond is broken, carbocation is resonance stabilized or back bonding stabilized, so there will be no shift or no rearrangement. After that water will attack and H positive will lose, and this will be the product of this reaction. And I want this and this, that you practice or you practice these questions. I hope you will answer these questions. Now compare the reactivity. How will you compare the reactivity? You just form a carbocation over here by removing X, carbocation over here. Similarly, you just remove carbocation over here, and after that you remove carbocation over here. After that, this shows plus M effect, this shows plus M effect, this shows plus H effect, and this shows minus what we call M effect. First of all, you have to write down plus M. Electron donating will stabilize the carbocation. That means first of all you will write 4, after that you will write 3, after that you will write down 2, after that you will write down 1. So this will be the stability order based on stability of carbocation. So more stable the carbocation, more will be the rate of SN1. Here, this bond will be broken and this will be the carbocation. This is anti-aromatic. Here, when this bond is broken, this will be the carbocation. This is non-aromatic. When this is broken, this will be the carbocation, and this is what we call anti-aromatic. Sorry, this is not anti-aromatic, this is aromatic. Now, aromatic with 2 pi electrons. We know aromatic is more stable than non-aromatic than anti-aromatic, so the answer will be 1, 2, and 3. So the answer is 1, 2, and 3. Here, when this bond is broken, positive charge is here, so it shows back bonding stabilized. But positive charge is here, there is no back bonding, but this will simply act as minus I group. This is back bonding here, more stable, minus I group. Here, this is also minus I with respect to this carbocation which will be formed over here. Now, minus I will destabilize the carbocation. This is closer, this is far away as compared to this. So the order will be simply back bonding, carbocation will be more stable. After that, weaker minus I, that means this one, and after that this one. We have already done this, plus I and minus I, or what we call resonance in GOC. So this will be the stability order, and this will be the rate of SN1 order as well. After that, stereochemistry of SN1 reaction. Have a look. If you are having a living group like this, and after that you are having, say for example, other groups like this. Now, this carbon is sp3 and is attached to 4 different groups, hence this is a chiral carbon or chiral center. Now, after that we know this halogen can be fluorine, chlorine, bromine, iodine, and fluorine, chlorine, bromine, iodine is having higher atomic number than carbon, deuterium or hydrogen. So this is having first priority because priority is directly proportional to atomic number. Then it is 2. Both these are having same atomic number. When atomic number does not help in priority, then priority is directly proportional to mass number. So this is 3 and this is 4. And 4 means least priority, 1 means highest priority. Least priority is on dash bond, that means behind the plane. Now have a look, 1, 2 and 3, that means this is S configuration. This chiral center is having S configuration. Now what will happen? What will happen? Now we know this step is a reversible step and a slower step. So when water, in presence of water, what will happen? Here will be, I mean to say, ionization or formation of a carbocation. Have a look. First of all, carbocation will be formed like this. So this is carbon. After that, carbocation will be formed and its bonds, say for example, will be like this. So one bond will be here. Other bond, say for example, is this. And another, let us suppose, is this. So this is the carbocation. And when this bond is broken, ionization takes place. Listen carefully. Ionization takes place, but when ionization takes place, listen. Ionization takes place. Have a look. Have a look. Or I will show like this. I will show in this fashion. I will show in this fashion. Have a look. This is the carbon. I will simply show like this, that one is R, another is D, say for example this is H. And X is basically bond between C and X is broken. But this leaving group, because of attraction with positive charge, is in close proximity with this cation. That's why these ion pairs are known as intimate ion pair or contact ion pair or tight ion pair. Basically, these are the positive and negative charged species are there. That means these are very close. This ion pair is not separated by solvents yet. So when they are not separated by solvents yet, solvent will come or a nucleophile will come. Say for example, water is the nucleophile. It will attack. It will attack to this carbocation. But when it wants to attack carbocation from that very side from which leaving group leaves, it will be repelled by this leaving group. That's why it will come from the opposite side. It will come from the opposite side. As this is a neutral nucleophile, finally H positive will be lost. So it will come from the opposite side to that of the leaving group. When it comes from the opposite side to that of leaving group, first it was sp2 hybridized. This is sp3 hybridized. It becomes sp2 in this. Now when fourth bond is formed with this nucleophile, it becomes once again sp3 hybridized, and the structure of the product will be like this. Structure of the product will be like this. Once again, it's a chiral center, sp3 hybridized. Now, if I write, no, it was not R, it is CH3. I will write down this as CH3. CH3, because the value of R was CH3. Now this is CH3. So 1, this is 2, priority, this is third priority group, this is fourth priority group, 1, 2 and 3. That means its configuration is R. Now, why this water cannot attack from that side from which leaving group wants to leave, yeah, leaving group leaves? Because leaving group has not left yet. It is in close proximity as that of cation. So they are very closer to each other. They are not what we call solvent separated. That's why when water wants to attack, when nucleophile wants to attack this carbocation, it cannot attack from that side where leaving group leaves, and that side is known as front side where leaving group leaves. That's why it attacks from back side. When it attacks from back side, means opposite side to that of this, there will be change in configuration at chiral center. That means change in configuration at chiral center means inversion takes place. So this is inversion. This is inversion. But after some time, water molecules or solvent molecules will solvate this ion, and they will separate these ions. When they separate these ions, that means this will leave at that time. Carbocation will be attacked at that time by nucleophile from front side as well as back side and in equal proportion. That means after some time, attack can be back side as well as front side. Now tell me. Now attack can be front side as well as back side. Have a look. This is 1, this is 2, priority third, priority 4. This is chiral center, sp3 hybridized. So 1, 2, 3. That means its configuration is S. So its configuration is same as that of what we call our reactant. So I will simply say retention of configuration has been taken place. So in short, what will happen during SN1 reaction? There will be inversion, that means backside attack of a nucleophile, as well as retention, that means front side attack of the nucleophile. Now the question is, when it was intimate ion pair or contact ion pair, only backside attack takes place. But when this ion pair becomes solvent separated ion pair, both attacks will take place equally. So first inversion, after that inversion, retention equally. That means backside attack will be more as compared to front side attack. That clearly indicates, as we know, these two, if we separate these two by means of a mirror, these two are what we call non-superimposable mirror images. That means here enantiomers are formed. So I can simply say these are enantiomers. These are enantiomers. But when enantiomers are formed in 50% and 50%, we call that as complete racemization or 100% racemization. But here racemization takes place, but that is not 100%, that is lesser than 100%. That's why we call this as partial racemization. So during SN1, what will happen? Partial racemization. Why partial? Why not complete? Because backside attack is more as compared to front side attack. And the reason for backside attack is intimate ion pair formation. Remember, intimate ion pair formation hinders what we call nucleophile to attack from front side. That's why it first attacks from back side. After some time, when this ion pair is solvent separated, at that time front side and back side will be equal. So in nutshell, in total backside attack or inversion will be more as compared to front side attack. That's why this is partial racemization. So why partial racemization takes place? Because inversion is more than retention. And the reason is intimate ion pair formation. Now tell me, if I want to increase racemization, what does that mean? That means if I want to decrease inversion, so that retention and inversion almost becomes equal. At what time retention and inversion becomes almost equal? If ion pair is not intimate, if ion pair is solvated, at that time chances of racemization will be more. So can I say racemization will be more when ion pair is solvent separated. What does that mean? Have a look. Now if I take, say SN1, if we do SN1 reaction of substrate in which there will be two, carbocations. One carbocation is less stable, another is more stable. Remember, if carbocation is more stable, that means its reactivity with nucleophile will be lesser. If reactivity of carbocation with nucleophile will be lesser, That means nucleophile will attack carbocation or carbocation will react with nucleophile after some time. But if nucleophile and carbocation interacts after some time, at that time this carbocation and halide ion will be separated due to solvent, or at that time it will be simply solvent separated ion pair. And if it is solvent separated ion pair, racemization will be more. Hence, simply you just remember these two formulas. Racemization will be more if reaction takes place after some time, if attack of nucleophile and carbocation takes place after some time, and it is possible only if carbocation is more stable. That means it is directly proportional to stability of carbocation. Number one. This is factor number one. So this is the factor affecting racemization. Second point is racemization will be more. Racemization will be more. But if attack of nucleophile takes place after some time, that means if nucleophile is not more stronger, that means it is inversely proportional to nucleophilicity. So if nucleophile is weaker, attack of nucleophile on carbocation will take some time. Till that time there will be an ion pair which is solvent separated, and if ion pair is solvent separated, racemization will be more, because attack at that time will be from back side and front side equally. Similarly, if stability of carbocation is greater, if carbocation is more stable, at that time carbocation will not react with nucleophile immediately, it will react after some time. That clearly indicates till that time ion pair will be a solvent separated ion pair, and hence racemization will be more. So remember these 2 points as well. So this is point number one and this is point number second. Now tell me, is this clear till now? Now let me know in the chats, is this clear till now? Because these are very, very, very important points. Are you getting me? Let me know in the chats. Are you getting me? Let me know in the chats. Quickly, my dear students, my dear lovely students, let me know in the chats. Are you with me? Are you focusing on the today's session or not? Let me know in the chats. Is this clear? Everyone, let me know in the chats. Is this clear? Is this clear? Serene, yes sir. Others please. Others please. I want reply from others. Sadab, but yes sir, all clear. Others. Quickly, let me know in the chats quickly. Is this clear till now? Yes sir. Okay. Now, after that, we are having SN2 reaction. What is SN2 reaction? SN2 reaction is simply substitution nucleophilic, substitution nucleophilic bimolecular reaction. Now, what is meant by this? That means it's that reaction for which rate is directly proportional to molar concentration of the substrate and molar concentration of nucleophile. So, it is equal to K into molar concentration of substrate and molar concentration of base. What is this K? This is rate constant. So, this becomes our rate law equation. Now, this is point number one. And from these points, it's clear that our reaction depends on two different types, say substrate and this. So, this becomes what we call a bimolecular reaction. Bimolecular reaction, as well as this concentration term is having coefficient of 1. Here its stoichiometric coefficient is 1. So, 1 plus 1 is 2. That means it is having second order kinetics, or this is simply a second order reaction. It's simply second order reaction. Point number next is, this reaction is single step reaction. It is a single step reaction. And what we call is believed. Let me write down first this, and is concerted. Concerted means, that means bond breaking and bond making takes place simultaneously. So, single step reaction and is concerted. Then it is believed to occur. It is believed to occur via transition state. That clearly indicates there is no intermediate carbocation. So no intermediate carbocation is formed. Hence, no rearrangement. Hence, no rearrangement takes place. So there will be no rearrangement as there is no intermediate carbocation. Now have a look. Now have a look. Have a look. Have a look. So for example, if you are having a structure like this, CH3X, or I will write down like this. This is H, this is C, this is H, and this is X. This is CH3X. Now, in one step, what will happen? Nucleophile will simply attack. Nucleophile. Let us say, for example, nucleophile is OH minus. This nucleophile will attack from backside, and this X minus will leave. Now the question is, why from backside? Why not? Why opposite side to that of leaving group? Why not? Why this nucleophile will not attack from the same side as that of X, as that of leaving group? Because as we know, this is the bonding molecular orbital. This bonding molecular orbital, to opposite to that is anti-bonding molecular orbital. And this anti-bonding, let me show you like this. This is OH minus. This is its negative charge, and negative charge is always, this is nucleophiles negative charge, and nucleophiles electrons are present in highest occupied molecular orbital. And of this C, this is, the bond or bonding orbital. Now, this is its anti-bonding molecular orbital. Have a look. This is bonding molecular orbital, and this is anti-bonding molecular orbital. As anti-bonding molecular orbital is empty. Now it will donate its electron to anti-bonding molecular orbital, and this anti-bonding molecular orbital is known as LUMO. So here will be HOMO, highest occupied molecular orbital, and lowest unoccupied molecular orbital interactions. So it will only possible from the back side. It will not possible from front side because there is orbital which is completely filled. That's why it attacks from the back side only. When it attacks from the backside, let me rub this one. So it will attack from the backside, and this will leave. That means here will be formation of a transition state, and transition state will be like this: C, H, H, and H at a degree of 120 degree. Now this bond will be broken, and this bond will be formed. So here it's a partial negative charge, it's partial negative charge. This is what we call a transition state. Now have a look. Carbon which is involved in substitution of transition state is pentacoordinated. It is pentacoordinated. 3 are normal bonds and 2 are partial bonds. Number 1 point. Number 2 point, its hybridization is sp2. Remember, its hybridization is sp2. It's pentacoordinated. Hybridization is sp2. And geometry is trigonal bipyramidal. Now, this is the slowest step. Hence, RDS, rate determining step. After this, what will happen? Reaction is very fast because this is highly unstable. So this will be like this. Here it will be H, 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 and OH will be like this. So we simply say that X, instead of X, there will be a nucleophile, and reaction is believed to occur via a transition state. Transition state is simply the representation which tells us which bond is broken and which bond is formed. So this bond is simply broken. So X minus will leave and COH bond will be formed. So this becomes bonding molecular orbital. I hope this is clear till now. After that, we are having factors affecting SN2 reaction. Now have a look. Example number 1. If you are having CH3, CH2X, have a look. Or I will write down like this, CH3X. So this is alpha carbon with respect to leaving group. After that, it is CH3, CH2X. This is alpha carbon with respect to X. After that, we are having secondary alkyl halide like this, CH3, CH, CH3 and X. And finally, we are having tertiary alkyl halide. We are having tertiary alkyl halide. Have a look. Now, Can I say here in first case it's X attached to carbon, and after that OH or the nucleophile, let me write down Nu minus, will attack from backside. That means from opposite side with respect to that of leaving group. Now, have a look. If we are having this one, that means at alpha carbon now alkyl group is present. This alkyl group is bulkier as compared to hydrogen. That means this nucleophile will attack but feel little hindrance due to this CH3 group. Now, if another CH3 group is there, C, CH, H, H, now similarly C, H, 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 and then X. So because of this and this, there will be more hindrance to the nucleophile. Here hindrance was because of one alkyl group, here hindrance is because of two alkyl group, and here hindrance is because of three alkyl groups. So more the number of alkyl groups at alpha position with respect to leaving group, remember, more will be the hindrance to the nucleophile. More the hindrance to the nucleophile, lesser will be the rate of SN1. So here hindrance is very large, so there will be no attack of nucleophile at all. So more the hindrance, lesser will be the rate. So that's why a number of alkyl groups at alpha or beta position with respect to leaving group is inversely proportional to rate of SN2. That means in such conditions, rate of SN2 will be decreased. So I will rub this or simply I will write down the answer over here. It will be simply methyl halide greater than 1 degree alkyl halide, after that 2 degree alkyl halide, and lastly 3 degree alkyl halide, or we can simply say 3 degree alkyl halide do not show SN2 reaction because of more hindrance. So this is the what we call order of SN2 reaction. I hope this is clear to you all. Now I can simply write down that this will not prefer SN2 reaction at all. So it is methyl halide, then this, then this, then this. In nutshell, more the number of alkyl groups at alpha position, lesser will be the rate of SN1. Similarly, if you are having like this, CH3, then it is CH2, then it's X. That means 1. This is alpha, this is beta. Now after that, I will increase alkyl groups at beta position. I will increase alkyl groups at beta position. Have a look. I will increase alkyl groups at beta position. What will happen? When alkyl groups at beta position is increased, hindrance or steric repulsion increases. So like that of alkyl groups at alpha position, when they increase, rate of SN1 decreases. Similarly, if alkyl groups at beta position increases, there will be also decrease in rate of SN1. So rate of SN2. Rate of SN2 order will be 1 greater than 2 greater than 3 greater than 4. Why? Because in case of 4, there will be more repulsion due to more alkyl groups at this. This is known as neopentyl halide. This will not even show SN2 reaction because of more repulsion. So more repulsions will be due to more alkyl groups either at alpha or at beta. So whenever alkyl groups are increased at alpha and beta position with respect to leaving group, there will be lesser SN2 reaction. I hope this is clear. Now, after that, effect of leaving group. Have a look. It is directly proportional to rate of SN2 reaction. What does that mean? That means if you are having leaving group like Ri, if are you having substrate like Rbr, RCl and Rf, we know, we have seen it that I minus is a good leaving group. I minus is a good leaving group than Br minus. Br minus is good leaving group than Cl minus. Cl minus is good leaving group than F minus. So this is a leaving group ability order. So if this is leaving group ability order, so greater the leaving group ability order, greater will be the rate of SN2. So rate of SN2 will be like this. So leaving group, good leaving group, so rate will be more, or weak leaving group, rate will be less. So rate is SN2 is directly proportional to leaving ability of the group. It's directly proportional to, so it is directly proportional to leaving ability of the group. Directly proportional to leaving ability of the group. I hope till now this is clear to you. Now after that, presence of electron withdrawing group. Have a look. If you are having CH3, CH2X, and you are having NO2, CH2, and then CH2X. Have a look. What will happen? What will happen? Nucleophile basically attacks, nucleophile attacks electron deficient site. Here it will attack to this and this will leave. But here it will attack to this and it will leave. Due to presence of electron withdrawing group, this becomes more deficient. If this becomes more deficient, say for example, this reaction takes place with a rate of R1 and this is R2, we will always say that a rate of R2 will be greater than R1. Why? Because remember, presence of what we call electron withdrawing group increases rate of SN2 reaction. Why? Because it simply withdraws electron and it simply increases electron deficiency of this carbon. More the electron deficiency at alpha position, more easily nucleophile will attack. After that, its effect of nucleophile. First, we will see strength of nucleophile. Strength of nucleophile. Remember, it is simply rate of SN2 is directly proportional to strength of nucleophile. More stronger the nucleophile, faster will be the SN2 reaction. So it is directly proportional to strength of nucleophile. Say we are having example, let's take an example of this, CH3X plus OH minus, and another example CH3X and then OR minus. Now have a look. This reaction will take place like this and this will take place like this. And remember, if this reaction is having rate R1 and this is having R2, we will simply say R2 greater than R1 because OR minus is a stronger nucleophile than OH minus. It's a stronger nucleophile than OH minus, or let me write NH2 minus. NH2 minus is a stronger nucleophile than OH minus. So because of this, rate of reaction will be more stronger the nucleophile, more will be the rate of SN2 reaction. Another is concentration of nucleophile. Another is concentration of nucleophile. Remember, more the concentration of a nucleophile, more will be the SN2 reaction. So it is directly proportional to concentration of nucleophile. So, for example, if I take CH3X and nucleophile at that time is OH minus, but it's having 1 molar concentration, and number second CH3X, and I will take nucleophile of 0.01 molar concentration. Now what will happen? What will happen? This will attack, this will attack, this will attack, this will attack to this and X will leave, this will attack to this, X will leave. But if this is having rate R1 and this is having rate R2, we will simply say R1 is greater than R2. Why? Because here concentration of nucleophile is more. So more the concentration of a nucleophile, more faster will be SN2 reaction. I hope this is clear to everyone. Now let me know in the chats, is this clear till now? Let me know in the chats, is this clear till now? Let me know in the chats, is this clear till now? Let me have a sip of water. Now let me know in the chats, is this clear till now? Let me know in the chats, is this clear till now? Quickly. Let me know, guys. Let me know. Is this clear? Yes, sir, it's clear. Okay. Now, after that, next is presence of pi bond at alpha position with respect to leaving group. Once again, we are talking about vinyl halide and aryl halide. Have a look. Have a look. Now, when nucleophile attacks this, it is very difficult to break this bond. Once again, because of partial double bond character. So that's why aryl halides and vinyl halides neither undergo SN1 reaction nor SN2 reaction, because it's very difficult to cleave their CX bond, as this bond is stronger due to partial double bond character as a result of resonance. So whenever this condition is there, remember it disfavors SN2 reaction, or it disfavors rate of SN2. I hope this is clear. Now, after that, presence of pi bond at beta position with respect to leaving group. Have a look. If you are having, say for example, pi bond like this at a beta position with respect to leaving group. Now, say for example, this is the nucleophile. What will happen? Nucleophile will attack to this alpha position and we have pi bond at beta position. Now, have a look. Here, transition state will be formed like this. Here, transition state will be formed like this. Say for example, transition state is like this. Say we are having this. Let me show like this. Suppose nucleophile forms bond over here. Suppose. So this is having partial negative charge, and suppose leaving group leaves from here. So this is having partial negative charge. I mean, say this, I have to write down this X over here. So don't worry about that. Now, after that this is having two hydrogen atoms, and after that we are having this CH double bond CH2. What is meant by CH double bond CH2? That means it's having this basically orbital and this orbital which has overlapped. So I can remove this double bond over here. I can show overlap over here. So these orbitals have basically overlapped together. So this is what we call our transition state. Have a look towards this transition state. This orbital and this orbital, they are in conjugation. That means parallel and within the same plane with respect to each other. If they are in conjugation with respect to each other, so I can simply say this is transition state is stabilized. Transition state is stabilized due to conjugation. That means transition state is stabilized due to conjugation when there is pi bond at beta position with respect to leaving group. If transition state is stable, we know rate of SN2 is directly proportional to stability of transition state. So remember, that means this condition increases rate of SN2 reaction. But let me tell you, polar pi bond at beta position shows more SN2 as compared to non-polar pi bond. Both increases actually rate, because both are resonance or what we call stabilized due to conjugation. So non-polar pi bond as well as polar pi bond at beta position increases rate of SN2 reaction. But among these two, which will increase more? It is simply polar pi bond, because if it is polar pi bond, that means between carbon and oxygen, say for example, then this oxygen in carbon, oxygen is more electronegative, it will withdraw its sigma electrons and carbon will acquire a positive charge. One, it is resonance stabilized or conjugated, this is conjugated transition state. Another, as this is having a positive charge, it will withdraw electrons. As this is negatively charged or what we call anion like transition state becomes more stable. So if polar pi bond is there, one is it is stabilized due to conjugation. Another, this is having partial positive charge, and this anion or negatively charged like transition state will be more stabilized due to this positive charge electron withdrawing nature. Now, another is presence of leaving group at bridgehead position. Once again, have a look. Whenever you are having leaving group at bridgehead position, simply this is a tertiary, at that time tertiary carbon, or this is tertiary halide, and we know tertiary, to attack tertiary carbon there will be more repulsion. That means nucleophile will not attack tertiary carbon as it will feel more repulsion. Hence, such simply disfavors, such condition disfavors SN2 reaction. So disfavors SN2 reaction. Simply disfavors SN2 reaction. That means this will neither show SN1 nor will show SN2 reaction. After that, it's effect of solvent. Effect of solvent. Now, have a look. Now, if you are having a reaction like this, if you want to simply replace this Br with the help of NaI, with the help of, say for example, methyl bromide is treated with NaI but in non-polar solvent. Non-polar solvent cannot ionize this ionic compound. That means there is no formation of I minus. So if there is no formation of I minus, rate of this reaction will be low. Suppose rate of this reaction is R1. Now, what will I do? I will change the solvent. I will take polar solvents. I will take polar solvents, and in polar solvent, what will happen? This NaI will be ionized. NaI will be ionized. That means there is formation of a nucleophile, and nucleophile will attack. NaI will be ionized. But first, I will take this in polar protic solvent like water. And then I will take this in polar aprotic solvent like DMF. Like DMF, DMSO, acetone, HMPA. Take. Now, what will happen? We know these types of solvents cannot solvate I minus, but water will solvate I minus. That means this will be solvated, this will be solvated, this is not solvated. So this will be solvated. So this will attack, but solvents will simply decrease the rate. This is free. This is not solvated, not solvated. So can I say this is free? Can I say this is free anion or free nucleophile? This free nucleophile will attack. That means if this is showing R2 reaction, rate of this reaction is R2, and if rate of this reaction is R3, what will be the rate of the reaction overall? R3 will be faster as compared to R2, and R2 will be faster as compared to R1. Or we can say this will not favor, say SN2 reaction. But among these two, which one will be more favorable? That means this one. So can we simply say, nutshell, polar aprotic solvents favor SN2 reaction. So remember, polar aprotic solvents favor SN2 reaction. I hope this is clear to you all. Why polar aprotic solvents? Because in these solvents, nucleophile will be formed, because this ionic compound will be ionized, nucleophile will be formed, and this nucleophile is free to attack electron deficient site. Nucleophile is formed, but this is not free to attack this electron deficient site because of solvation. Now, after that, there are few questions. Compare rate of SN2 reaction. Have a look. This is alpha. At alpha, hydrogens are there. At alpha, one alkyl group is increased. At this alpha, two alkyl groups are increased. At this alpha, three alkyl groups are increased. 1, 2, 3. We know more the number of alkyl groups at alpha or beta position, lesser will be the rate. So rate of this reaction will be 1, 2, 3 and 4. I hope this is clear to everyone. After that, now this is vinyl halide, this is benzyl halide, and that is this. Now have a look. We are having pi bond at alpha position, it will not favor, and we are having pi bond at beta position here, pi bond at beta position here. But this is polar pi bond, this is non-polar pi bond. So first polar pi bond, then non-polar pi bond, then this will be at the last. This will even not favor what we call SN2 reaction. After that, next is SN1 versus SN2. Have a look. Whenever you feel difficulty whether this substrate shows SN1 or SN2, this is simple. Methyl halides always show SN2. Methyl halides always show SN2. Primary alkyl halides show SN2. Always. There is no doubt. And tertiary alkyl halides prefer SN1. So among SN1 and SN2, it will prefer SN1. These two will prefer SN2. So the only is secondary alkyl halide where both can take place. So here will be the possibility that we may simply do, say some mistakes. So for that purpose, have a look. If you are having secondary alkyl halide and you are having strong bases like Na positive and Cn minus, this is strong nucleophile. Cn minus, negatively charged nucleophiles are stronger nucleophiles in general. So CO minus R, O minus. So whenever you are having stronger nucleophiles, at that time SN2, at that time secondary alkyl halide will prefer SN2 reaction. And if you are having neutral nucleophiles, weaker nucleophiles, then secondary alkyl halide will prefer SN1 reaction. But here this is 1 degree. This is 1 degree because this is 1 degree carbon to which halogen is attached, 1 degree carbon to which halogen is attached, 1 degree carbon to which halogen is attached. But it will generally prefer SN1. Why? Because they result in the formation of stable carbocations, back bonding stabilized and resonance stabilized carbocations. That's why they prefer SN1 reaction. After that, here are a few questions. Now have a look. Complete the following reactions. Now, water is there and this is secondary alkyl halide. Water is there. Have a look, have a look, have a look. Water is there and secondary alkyl halide is there. So this will be SN1 reaction. So this will be SN1 reaction. Now remove this, form a carbocation, hydride shift, form carbocation here and OH will go there. Similarly, tertiary alkyl halides. Have a look. Have a look, have a look, have a look. Tertiary alkyl halides always show SN1 reaction. That means this is SN1 reaction. This is SN1 reaction. Among SN2 and SN1, this is SN1. This is once again a tertiary alkyl halide, so SN1 reaction. So you have to remove this X, form a carbocation, OH will attack, form a carbocation, OCH3 will attack, negative part. Negative part is not OH. H is positive and negative part is OCH3. So I hope you will form the products as well. Now, have a look. Whenever you are having NaOH aqueous or KOH aqueous, that means it is OH having negative charge. That means it's a stronger nucleophile, so it will prefer SN2 with secondary alkyl halide. So simply you have to remove Cl and attach OH there. Here, this is what we call wedge. That means here Br is above the plane. Now, what you have to do is, this is once again SN2, but as it is here above the plane, that means stereochemistry is discussed. So you have to attach. This reaction is SN2 reaction. You have to attach, say nucleophile from the opposite side. Why? As this is above the plane, nucleophile will attack from below the plane. That means opposite side. Nucleophile always attacks opposite side. That means inversion will take place. Now, what will happen over here? This is the nucleophile, though this is the leaving group. Nucleophile will attack from opposite side. That means this one. At chiral center, nucleophile simply reverses the configuration or inversion takes place at what we call this chiral center. So this is the chiral center. 4 different groups are attached. Br will replace this OH will replace Br, but OH will attack from opposite side. So this is once again SN2 reaction. So during SN2 reaction, there is always backside attack taking place. That means 100% or complete inversion takes place. Now, one second guys, 1 second. Okay, we don't this. Okay, but before elimination, let me show you stereochemistry of SN2 reaction. So during SN2 reaction, complete backside attack takes place or 100% backside attack takes place. That means complete inversion takes place. Have a look. If you are having C, you are having, say for example, CH3, you are having D, and you are having H, and you are having X. So this is priority number 1, priority number 2, priority number 3, priority number 4. This is the chiral center, sp3 hybridized center. Its configuration is S. Nucleophile will always attack. Nucleophile will always attack from backside because this is having empty anti-bonding molecular orbital over here. And second reason, it cannot come from this side because electron cloud of X will repel this electron cloud of nucleophile. Now, So here HOMO of nucleophile and LUMO of this, I mean say this electron deficient site, they will interact with each other and result in the formation of a bond. So it will result in the formation of a bond like this. So OH negative and X want to leave with a negative charge, and here it will be CH3, then it will be D, then it will be H. So a transition state will be first formed, and this will be the slowest step and hence rate determining step. After that, a very fast step takes place. I mean say basically transition state once formed is very unstable and it gets converted to the product, and the product will be formed like this. This will be COH, here it will be CH3, then it will be D, then it will be H. So this is the chiral center, once again sp3 center. So priority will be like this, and it will be 1, 2, 3, that means configuration will be R. So at chiral center, configuration is inverted. Only backside attack will take place, front side attack will not take place. That means here complete inversion or 100% backside attack or inversion takes place. And this inversion is known as, and this inversion is sometimes called umbrella inversion. Umbrella inversion. As this, I mean say, configuration of this chiral center is inverted. Configuration of this chiral center is inverted. That means these groups have been inverted like or in the similar manner as that of umbrella when it turns inside out when it's caught under strong winds. So it's like that of umbrella, that's why umbrella inversion, or it is simply known as Walden inversion. So 100% Walden inversion, 100% backside attack or 100% inversion takes place. So whenever you are having stereochemistry, whenever you discuss stereochemistry, you have to attack nucleophile from the opposite side to that of leaving group. So if leaving group here was above the plane, you have to attack that chiral center. First of all, you have to look, is this a chiral center? So you have to attack chiral center from opposite side. Similarly, this is the chiral center. So you have to attack chiral center from opposite side. Have a look. This is 1, this is 2, this is 3, and this is 4. Its configuration was S, 1, 2, and 3. And here, this is 1, this is 2, this is 3, this is 4, its configuration is R. So configuration at chiral center is reversed. So this is what we call stereochemistry of SN2 reaction. After that, we are having elimination reactions, and we have already discussed elimination reactions in hydrocarbons. So let me show you this E1 and E2. You have to, study E1 and E2 only. Not necessary, you don't want E1 CB, you don't want Hoffman's elimination or internal or intramolecular elimination. So I have already written over here what we have already studied. So remember, E1 means elimination unimolecular reaction, and for that rate is directly proportional to substrate, or rate is equal K in substrate. Now, because of this it's unimolecular, because of this first order, it's a multi-step reaction. First step is ionization step, that means formation of carbocation. As intermediate is carbocation, there will be always chances of what we call rearrangement. So after that, rate of E1 is directly proportional to stability of a carbocation in rate determining step, and rate of E1 is directly proportional to leaving ability of the group. Similarly, rate of E1 is directly proportional to dielectric constant value of the solvent, and number of products formed is equal to number of different types of hydrogens at position adjacent to the most stable carbocation. That means products can be Huffman, product can be Sadzip, but remember, during E1, Sadzip product is always major product. Say, for example, you are having like this, CH3, CHX, CH2, CH3. And if you are doing E2 reaction, E1 reaction over here, and elimination reaction generally favored by high temperature. Why? We will not deep dive into that concept first. Now, you simply remember, as time is very less. Now, here I will show you that during E1 reaction, what will happen? First of all, it will lose this CX bond and will result in the formation of a carbocation. First step is formation of a carbocation. After that, rearrange carbocation if rearrangement is possible. Here, rearrangement is not possible. So, next step will be simply base or this solvent will act as a base, or base will come, and that will simply remove hydrogen from the position adjacent to the carbocation. If you look towards this position adjacent to the carbocation and this position adjacent to the carbocation, these are two different positions. This is rich with respect to hydrogens and this is poor with respect to hydrogen. When we abstract hydrogen from a rich position, it will result in the formation of CH2, double bond CH, single bond CH2, single bond CH3. And this is less alkylated alkene, hence Hofmann product. When this hydrogen, and a hydrogen from poor position is abstracted by means of a base, it will result in more alkylated alkene, that means ZF product. And during this, what we call SN1 reaction, ZF is always major product. So this is the major product and this is minor product. Now, after that E2, we have already discussed E2 in detail. These are few points which are written over here. Now, after that, we know during E2, ZF product generally predominates, but there are few conditions where Hofmann as well as ZF will be the major product. Like if leaving group is poor, you have to check whether Hofmann is stable or ZF is stable. If you have not studied hydrocarbon, I request you all that go through that hydrocarbon chapter. You will see all these conditions. Now, after that, we are having next, that is substitution versus elimination. Have a look. If you are having a neutral reagent, remember it can be a weaker nucleophile or a weaker base. And if it is weaker nucleophile or a weaker base, then SN1 or E1 will take place. Similarly, if you are having negatively charged reagent, then at that time it's a stronger nucleophile or a stronger base. If it is a stronger nucleophile, then SN2. If it is a stronger base, then E2 reaction will take place. Now, you will remember this table, but I will show you a few examples so that you can understand easily. Now, have a look. As this is negatively charged is a stronger nucleophile as well as a stronger base. Now, negatively charged reagent can be a stronger nucleophile as well as a stronger base, as this is stronger nucleophile as a stronger base. But if it acts as a nucleophile, it will attack to this, Br will be lost. That means product will be like this. And this product will be SN2 product. Why? Because stronger nucleophile will show SN2 reaction. After that, if it acts as a base, then it will be E2 reaction. So this is alpha, this is beta. From alpha, leaving group will leave. From beta, hydrogen will leave. So this will be the, say E2 product. And other will be CH3, OH, Br minus, those will be the side products. Now, have a look. When you see its percentage is approximately 90% formed, it will be approximately 10% formed. What does that mean? That means whenever you are having a strong reagent and your 1 degree alkyl halide is unhindered, it generally prefers SN2 reaction. Similarly, if you are having strong reagent but your alkyl halide is having branch, that means there is repulsion. So nucleophile will feel repulsion. At that time, if it acts like a nucleophile, its product will be like this. But if it acts as a base, then product will be like this. That means this will be SN2 reaction, this will be E2 reaction. But at this time, this is only 40%, this will form 60%. That means this will be major and this will be minor. Now have a look, This will be major, here this will be major. Now, at what time SN2 will be favored and at what time E2 will be favored? If alkyl halides are primary and reagents are strong. If primary reagent is without hindrance, without branch, then SN2 will favor with strong reagents. And with strong reagent, E2 will be favored if either primary alkyl halide is having branch or base or reagent, strong negatively charged reagent is having what we call branch. Now here, this is having branch, here this is having branch. But if it acts as what we call strong nucleophile, it will show a reaction like this. It will be O and then this. That means it will be a SN2 product. Now after that, if it will act as a base, product will be like this. Product will be like this and this will be the E2 product. Now have a look. Whenever you are having branch in either alkyl halide or you are having branch in base or a branch in what we call reagent, then at that time this alkyl halide, primary alkyl halide is not having any branch. So whenever you are having primary alkyl halide and a reagent, both does not have any branch, there will be no steric repulsion, so SN2 will be favored if this is negatively charged. But if this is negatively charged, but primary alkyl halide, either primary alkyl halide is branch or base is branch, at that time SN2 will be favored. At that time SN2 will be favored. So have a look. This will become major at that time and this will become minor at that time. Approximately this will become 85% or that will become 15% approximately. Now have a look. When you are having a strong reagent, this was when primary alkyl halide is there. If you are having strong reagent and you are having a secondary alkyl halide, at that time it will act as a base as well as a nucleophile. So this will be as nucleophile, so this will be SN2, and as base it will be E2. And remember, at that time E2 will be favored. So E2 will be the major product. A2 will be major and this will be minor. Let's suppose this is having 25% and that will be having 75%. So have a look. Now this is a strong nucleophile. Negatively charged acetate ion is stronger nucleophile, but it's a weak base. Now as it is weak base, it will favor SN2 reaction. If it will favor SN2 reaction, it will not favor E2 because it's not a good base. So this will be the product and that too will be 100%. It will not favor E2 as it is weaker base. Now this will favor SN2 E2, but as this is tertiary alkyl halide does not undergo SN2, so it will undergo simply E2 reaction. So this will be 100% E2. This is E2 product and this is SN2 product. Now have a look. This is weaker nucleophile. And this is tertiary alkyl halide. Tertiary alkyl halide and weaker nucleophile, either SN1 or what we call E1. Either SN1 or E1. So first of all, it will break. So it will result in the formation of a carbocation. When it forms a carbocation over here, here will be simply this O will attack and after that CH3. So OCH3 will be attached. OCH2CH3 will be attached to this. OCH2CH3 will be attached to this. So this will become the SN1 product and E1 product. E1 product will be like this. This will become E1 product. But remember, among SN1 and E1, SN1 will be always faster reaction. Rate of SN1 will be always fast as compared to, greater as compared to E1. What is the reason? Have a look. First of all, carbocation will form. In case of SN1, nucleophile has to form only one bond with this. But if it acts as a base, it has to break one bond at beta and after that it has to form double bond between alpha and beta. That means one bond has to be broken and another has to be formed. That means it has to first break and then make another bond. But as nucleophile, it has to only form bonds. So number of bonds formed will be, that means rate will be simply faster when it will show SN1 reaction. So this is what we call SN1 and E1, SN2 and E2 in nutshell, elimination versus substitution. Now, let us start our chapter now. So these were few basics which we will need in this chapter. So let us start our chapter. So from alcohols, first of all, alcohols, we have to prepare alkyl halide or haloalkane from alcohol. What we have to do? We have to replace this OH by X. That means from alcohols, whenever you have to form RX from alcohols, these types of reactions are nucleophilic substitution reactions. Now, when alcohol is treated with HX, whenever alcohol is treated with HX, remember, we will simply form, we will replace this water OH and H, and instead of OH I will write down X. That means It's once again a nucleophilic substitution. It will be once again a nucleophilic substitution reaction, but this reaction generally takes place via SN1 mechanism. But primary alcohols undergo this reaction via SN2 mechanism. So only primary alcohols can show this reaction via SN2, but other alcohols generally show this reaction via SN1. As this reaction is generally what we call SN1 reaction, so we can simply say among alcohols, rate of this reaction will be simply, rate of this reaction will be 3 degree alcohol greater than 2 degree alcohol greater than 1 degree alcohol. Remember this. So rate will be this one among alcohols, and among halogen acids or hydrogen halides, rate will be simply HI greater than HBr greater than HCl greater than HF. So you have to remember that rate of reaction among halogen acids will be like this, and among alcohols will be like this. Now, if our alcohol undergoes SN1 mechanism, then what will happen? First of all, as OH is not a good leaving group, this is a poor leaving group. First of all, protonation will take place. Protonation of alcohol takes place, and it will result in the formation of this oxonium ion. Now after that, this becomes a good leaving group. This is now a good leaving group. H2O with a positive charge is a good leaving group. Now it will leave, and this is what we call the slowest step of the reaction, or rate determining step of the reaction, that this water will leave and it will result in the formation of a carbocation. Now, as carbocation is formed, rearrange if possible. If rearrangement is possible, then we have to rearrange this carbocation first. Now, after that, nucleophile will attack. That means after that, this X minus will attack, and this attack is very fast. So this will attack and it will result in the formation of RX. Now, this is what we call if reaction takes place via SN1 mechanism. If reaction takes place via SN2 mechanism, what will happen? This ROH first, as this is not a good leaving group, it abstracts proton from halogen acid, and it will result first in the formation of ROHH with a positive charge. That means it will first form this poor leaving group to good leaving group. It will first form this from poor leaving group to good leaving group. Now, after that, remember this X minus will attack. X minus will attack to this electron deficient site, and this will remove. But when this R is primary, otherwise it can form secondary or tertiary, can form more stable carbocations. So any species which can form more stable carbocation undergoes reaction via SN1, and that which cannot form more stable carbocation like 1 degree, so it will prefer this SN2 mechanism. So it will result in the formation of RX, and here it will lose water molecule. I hope this is clear to everyone that it can either show SN1 or SN2, but generally it shows SN1 reaction. As it shows SN1 reaction, so rate of alcohol is directly proportional to stability of carbocation. That's why I have written over here that tertiary will show faster rate of this reaction as compared to secondary, as compared to primary, because it forms more stable tertiary carbocation as compared to secondary carbocation as compared to primary carbocation. Here we have to break HX bond. So as HX bond is easily broken over here in case of HI as compared to HBr, as compared to HCl, as compared to HF, so this will be the rate for this reaction. Now, after that, we have to write now this reaction of alcohol with HCl. We have to write down reaction of alcohol with HCl. Have a look. We have to write down reaction of alcohol with HCl. Now, if we are having 1 degree alcohol, and we need anhydrous zinc chloride at that time. We need anhydrous zinc chloride. But if reaction is taking place at room temperature, primary alcohols are very less reactive. That is the reason that there is no reaction. That is the reason there is no reaction taking place between primary alcohol and this. This is known as 1:1 mixture of HCl and zinc chloride is known as Lucas reagent. It's known as Lucas reagent. Have a look. Similarly, if I take secondary alcohol, and then I treat it with Lucas reagent at room temperature, zinc chloride anhydrous, what will happen? It will result in the formation of CH3. This OH will be replaced by Cl. That means it results in the formation of alkyl chloride. But when alkyl chloride is formed, there will be a cloudiness known as turbidity. So I can simply say turbidity appears. So as in this case, no reaction has been formed, taking place, no alkyl chloride is formed. So we can simply say no turbidity appears. No turbidity appears. Similarly, if I write down tertiary alkyl halide, tertiary alcohol, and treat it with Lucas reagent. Have a look. And try to understand. What will happen? Water will be lost. This OH will be lost, and instead of OH, Cl will take the place of OH, and it will result in the formation of tertiary alkyl chloride. In nutshell, alkyl halide will be formed, alkyl chloride will be formed. Hence, turbidity appears once again. But have a look. What is the difference between this second reaction and third reaction? As secondary alcohol is not that reactive, that's why turbidity appears after few minutes. But here turbidity appears immediately. That means turbidity appears in seconds. Turbidity appears in minutes. Now the question is, turbidity, rate of turbidity, can I say, is directly proportional to stability of carbocation. It depends upon stability of the carbocation. Have a look. As it can form tertiary carbocation, a very stable carbocation among these. That's why turbidity appears quickly. Similarly, if you form a carbocation which is resonance stabilized, back bonding stabilized, then or that will be a aromatic carbocation, that turbidity appears immediately or turbidity appears in seconds. Now have a look. So can I say, with the help of Lucas reagent, we can distinguish 1 degree alcohol, 2 degree alcohol and 3 degree alcohol. With the help of Lucas reagent, we can distinguish these. How? Because if we are having primary, secondary or tertiary alcohol in a test tube, but we don't know which type of alcohol is this, what will we do? We will drop, we will add simply Lucas reagent. When we add Lucas reagent, we will see if turbidity appears immediately, we will simply say this was the tertiary alcohol. But if turbidity appears after some time, after 5 minutes, 10 minutes, we will say this was secondary alcohol. If turbidity does not appear, we simply say this is primary alcohol. So with the help of Lucas reagent, we can distinguish primary, secondary and tertiary alcohol, and that test is simply known as Lucas test. So what is Lucas test? Lucas test is simply that test with the help of which we can distinguish primary, secondary and tertiary alcohol, and with the help of Lucas reagent. I hope this is clear to everyone. Next, primary alcohol can show the reaction. यानी primary alcohol can form what we call product, but not under room temperature, but upon heating it can result in the formation of what we call alkyl chloride, or it can result in the formation of turbidity, but upon heating. Number one, this is another point. Another point is tertiary alcohol can react with HCl. Tertiary alcohol can react with HCl without even zinc chloride, anhydrous zinc chloride, without help of Lewis acid, because it's very reactive and it can result in the formation of tertiary alkyl chloride. Now the question is, what is the function of anhydrous zinc chloride? What is the function of anhydrous zinc chloride? Remember, anhydrous zinc chloride basically helps in cleavage of CO bond. Have a look. Now, have a look. This lone pair can attack this Lewis acid. When it attacks Lewis acid, it will acquire a positive charge. More positive charge on oxygen means this bond will break easily, because it will withdraw electrons from carbon and will leave. That means it helps in cleavage of CO bond. Another point is reaction of alcohols with Lucas reagent to form alkyl chlorides is known as Grew's process. So whenever alkyl chloride is formed by reacting alcohol with Lucas reagent, that reaction will be known as Grew's process. Say for example, you are having few examples over here. So these reactions are SN1 reactions, and you will simply first form carbocation, and after that rearrange those carbocations if rearrangement is possible, and finally attach X- with that carbocation. Your product will be formed after that. But let me show you this reaction. This OH is attached to sp3, but this OH is attached to sp2. That means this OH will show here what we call a partial double bond character. That means this COH bond is very stronger. So to cleave this bond, it's very difficult to cleave this CO bond. So this OH and C bond is easily cleaved. Carbocation will be formed. And finally, when carbocation is formed, here you will simply attach X to that. Carbocation will be formed over here, X- will attach over here. So this OH will not be replaced. Whenever OH is attached to carbon-carbon double bond, that OH can never be replaced due to partial double bond character. That bond becomes very stronger. Now, after that, next reaction is reaction of alcohol with HBr. Have a look. Reaction with HBr. What will happen over here? Your alcohol can simply react with HBr, as HBr is a little more reactive than what we call HCl. So in presence of few drops of concentrated sulfuric acid, this reaction can also be done. So here OH will be simply, this OH will attack with this H, OH2 positive, and it will remove, and Br will attack. So it will result in the formation of RBr. But remember that if this is secondary or tertiary alcohol, you have to first form carbocation over here, you have to rearrange that, and after that Br will attack. But primary alcohol, remove OH, and instead of that OH, you just attach Br to that. So this will be the reaction. But HBr can be generated in situ. That means it's not necessary that we add HBr to alcohol. Sometimes HBr is generated within the reaction. Say for example, NABr is there, or KBr is there, and we add H2SO4. What will happen? Have a look. These two, have a look. These two will combine together, and it will form H positive Br minus, that means it will form HBr, and here Na positive and HSO4 minus. But among these two, HBr will react with OH. When HBr will react with OH, these two products will be formed. That means RBr and water will be formed. And this will not react, so it will remain as it is. So NaHSO4. So I mean to say, either we will add HBr to alcohol directly, or we will form this HBr. Have a look. We will form this HBr during the reaction. That's why I wrote in situ. Now, this is the reaction. Similarly, it's a reaction of alcohol with HI. Reaction of alcohol with HI. Have a look. When you react alcohol with HI, as HI is very reactive, so it will result in the formation of alkyl iodide. So reaction can be SN1, it can be SN2, depending upon alcohol, whether it forms a more stable carbocation or not. Similarly, this HI can also be generated. HI can also be generated in situ, during the reaction. So what will happen? Have a look. We will not add HI directly, we will add NaI or Ki. NaI or Ki, and we will use H3PO4, phosphoric acid, instead of H2SO4. We will not use H2SO4. Why? I will tell you the answer, but before that, just have a look towards the reaction. So H positive I minus, that means HI will be formed, and NaH2PO4. So this HI will react with OH like this, so it will result in the formation of Ri plus H2O plus. This will not react, so it will remain as it is. So it is NaH2PO4. Now the question is, why do not we use H2SO4? Remember, if we use H2SO4, have a look. If we use H2SO4, what will H2SO4 do in this reaction? It will first form HI and then NaHSO4. After that, this HI will be oxidized by H2SO4, as this is an oxidizing agent. It will oxidize this HI to I2, say for example twice, and as this is a reducing agent, and it will reduce H2SO4 to SO2 plus twice H2O. So I think hydrogens are balanced, oxygen is balanced, yes. So this is reducing agent, it will reduce this to SO2 and it will oxidize HI to I2. So there will be no HI at that time. If no HI is formed, so this H2SO4 cannot be used, as this is an oxidizing agent. That's why we use non-oxidizing what we call acid. After that, reaction with PCl5. Remember, if you are having ROH and PCl5, simple trick is there. So you write down PCl5 in this fashion. So after that, you will say it will result in the formation of HCl, it will result in the formation of POCl3, and it will result in the formation of RCl. So whenever you are having ROH plus PCl5, you have to remove this OH, and instead of OH, you have to add a nucleophile attached to phosphorus, that means RCl. Then another product will be POCl3. Another product will be HCl. And this RCl will be formed either by SN2 or SNI, but SNI is not in your syllabus, so we will focus on SN2. So therefore, there will be what we call inversion in configuration. I hope this is clear to you. Now, after that, now, give me a second. Now, next reaction is reaction with PX3. Whenever you are having alcohol and reaction of alcohol with PX3, at that time, you simply replace this OH by halogen. And another product will be H3PO3. If you want to balance the reaction, then it should be 3 times, it should be 3 times, then R will be balanced, X will be balanced, and PO3, everything is balanced. So for this you have a trick, like you have ROH, and then you have PX3. You have PX3, P, X, X, and X. You simply remove this one, that means H3PO3, and then RX, RX, RX. So it's like this, and this will be formed due to SN2 reaction. After that, you are having reaction with SOCl2. SOCl2 is known as thionyl chloride. Thionyl chloride. Now what will happen here? Simply, if you are having RX, if you are having ROH, alcohol, and you treat it with thionyl chloride, it will take place either in presence of pyridine as base or in absence of pyridine. So what will happen? Replace OH by Cl. So the product will be RCl plus SO2, it will be a gas, and HCl, it is also a gas. So side products are gases. So gases will evolve, and our alkyl chloride will be formed in pure form. But this reaction is SN2 and this reaction is SNI. Means here inversion of configuration takes place at chiral center. Here retention of configuration takes place at chiral center. You just remember only this in case of SNI. So this reaction is known as Darzon's procedure or Darzon's process. So Darzon's procedure. So this is Darzon's procedure. Now, and this reaction is considered. This reaction is considered as best method to prepare alkyl chloride, because here alkyl chloride will be obtained in pure form. As side products are gases, they will evolve. Now after that, we are having halogenation, reaction of alkane. This we have already seen in what we call hydrocarbon unit. So I hope you will study this reaction there. So in presence of light or heat, what we have to do is just replace this, so it will result in the formation of this. And this reaction is a free radical substitution reaction, and here X2 can be F2, Cl2, Br2, I2, but F2 is very reactive, that fluorination, direct fluorination is not possible. We simply use either chlorination or bromination, because if we take iodination, Hi will be formed and the reaction will be, irreversible due to formation of Hi that will convert Ri into alkane. So you just, we have already studied or discussed this reaction in hydrocarbons. After that, addition of halogen acids. Let me write down like this: alkene and then HX. We have already shown this reaction in hydrocarbons. This is electrophilic addition reaction taking place via classical carbocation. So what will happen over here? Here reaction will be like this. It will attack this and X minus will lose. First, it will result in the formation of a carbocation. So it will result in the formation of carbocation. Just after that, we have to rearrange. If rearrangement takes place, after that, this will attack over this, and this is the slowest step or rate determining step. And addition generally takes place according to Markovnikov's rule if unsymmetrical reagent is added to unsymmetrical substrate. And sometimes there may be the rearrangement. At that time, a rearranged product will be formed. So this is already discussed in hydrocarbons. Similarly, this is discussed in hydrocarbons. Here, reaction generally takes place by chlorine or bromine, and if we use bromine, then it can be used as a test for unsaturation. It can be either in, what we call non-polar solvent, or halogenation can take place in polar solvent. Here we simply form geminal dihalides, and this reaction is anti-addition reaction. Here product is halohydrin, and this is also an anti-addition product. This is electrophilic addition reaction taking place via non-classical carbocation. I request you all, you just go through hydrocarbon, you will see these types of reactions there. Now, halogen exchange. Number one is Finkelstein reaction. Finkelstein reaction. Now, first of all, you have to do that alkyl chloride or alkyl bromide reacts with either NiI, that means sodium iodide, or potassium iodide. Similarly, sodium iodide or potassium iodide. So, reaction of alkyl chloride or alkyl bromide in dry acetone. So, acetone is basically polar aprotic solvent, hence this is what we call SN2 reaction. So, what will happen? In acetone, these are soluble. That means nucleophile is generated over here. So, nucleophile will attack over this and this will lost. Similarly, the product will be Ri, that means alkyl iodide, and here either NaBr or KBr will be formed. But these are insoluble in dry acetone, so these will be these will be precipitated out. Similarly, this will be resulting in the formation of, this will be Na, not Br, this will be NaCl and KCl, and this will separate out as a precipitate. This will be NaBr or KBr, and NaBr or KBr, NaCl or KCl, these are insoluble in dry acetone, so this will separate out. Hence, it will facilitate, it simply facilitates, forward reaction according to Le Chatelier's principle. Yeah, simply this reaction is favored by Le Chatelier's principle. So, this reaction is favored by Le Chatelier's principle. So, what is Finkelstein reaction? Le Chatelier's principle. What is Finkelstein reaction? It is simply halogen exchange. Chlorine and iodine. Iodine will, say exchange chlorine. Similarly, iodine will exchange bromine. So, reaction of alkyl chloride or alkyl bromide with sodium iodide or sodium iodide or potassium iodide in dry acetone, so that halogen exchange will take place and alkyl iodide will form, and this reaction is SN2 reaction. Now, after that, second halogen exchange reaction is Schwartz process. It's Schwartz process. Now, have a look. If you are having alkyl chloride or alkyl bromide and you simply react them with heavy metal fluorides like AgF, HgF2, Hg2F2, SbF3, COF3, AsF3, etc. Heavy metal fluoride should be there. So, this is simply a reaction in which this chlorine or bromine is replaced by fluorine. So, it will result in the formation of alkyl fluoride, and this AgCl will precipitate out. Similarly, AgBr will precipitate out. So, this is Schwartz process. Now, after that, we are having methods of preparation of haloarenes. Number one is from aromatic hydrocarbon by direct halogenation. First is nuclear halogenation. Remember, this is an example of ESR reaction, electrophilic substitution reaction. Number second, this reaction takes place in presence of Lewis acid, and in absence of light. That means it takes place in darkness. So, if we are having, say for example, benzene, aromatic hydrocarbon, and if I treat this with X2 in presence of Fe and dark. First, Fe will react with X2 and result in the formation of FeX3. After that, FeX3 will react with X2 and it will result in the formation of FeX4 having negative charge and X positive. That means here X positive will generate, it will act as an electrophile. Now, electrophile will go to that position of this ring which is highly electron rich, but all the positions are having similar electron density, so it will go to any carbon. So it will result in the formation of aryl halide. Similarly, if you are having, okay, you can use what we call Lewis acids as well. If you are having this ones, toluene, and you are simply reacting this toluene with this one, once again, what will be the electrophile of this reaction? Electrophile will be once again X positive. So that X positive will go to either ortho position or to para position. Why? Because this CH3 donates electron to the ring due to plus H, hyperconjugation, and increases electron density at ortho and para. If it increases electron density at ortho and para, electrophile will go either to ortho or to para position. Now have a look. When one X goes to this, H will be replaced, so that H will go with another X, similarly this. Here, repulsion will be more, repulsion will be less, so this will be more stable, so this will be the major product and this will be the minor product. So, halogen is introduced within this, I mean say nucleus within this aromatic ring, that's why this is known as nuclear halogenation. So, this is first one, that is nuclear halogenation. Now, second is side chain halogenation. What will we do over here? First thing, that our aromatic hydrocarbon must contain some side chain having some hydrogen. Now, it's simply, first of all, it is simply an example of free radical substitution reaction. Number one. Number second, it takes place in absence of sunlight. In absence of light, it takes place in absence of light. In absence of Lewis acid, not light, in absence of Lewis acid and in presence of light. So these are the conditions with the help of which we can simply find out whether is this nuclear halogenation or side chain halogenation. Have a look. If it is X2 in presence of light, then it is what we call side chain halogenation. If it is X2 without light, it is a nuclear halogenation. Now what will happen? Due to this light, free radicals will be generated here. So X radical will simply break CH bond from the benzylic position and it will result a free radical at benzylic position. So this benzylic position forms a free radical first, as this radical is stable because of resonance, and after that X will go there. If halogen is taken in excess, then another hydrogen will be replaced by X, then after that another hydrogen will be replaced by X, so all the hydrogens will be replaced by X. Similarly, if we write down this CH2 CH3, have a look, as this is the free radical substitution reaction, so we know free radicals will be formed. Here free radical will be not formed, is not that much stable as free radical is stable over here. So that's why a halogenation generally takes place in side chain at benzylic position. Benzylic position means that carbon which is directly attached to benzyl, that benzene. So this will be the product over here. So halogenation will take place at benzylic position, not over here. That's why this reaction is also known as benzylic halogenation. Now generally this X can be either Cl or Br, that means we can have benzylic chlorination, benzylic bromination. So similarly this is also having Cl or Br. F2 is not used because that is explosive or uncontrolled reaction. I2 can be used but in presence of strong oxidizing agents like HiO4, like HNO3, like HGO, otherwise that will be a reversible reaction due to formation of Hi. Now after this reaction, remember this allylic chlorination can also be carried out by using SOCl2, like that of allylic halogenation, by using N-chlorosuccinimide, and allylic bromination, benzylic bromination can be taken place like that of allylic bromination by using NBS. So go through allylic halogenation in hydrocarbons, you will get what I was telling you here. Now after that, next is from aromatic amines. Have a look. Whenever you are having an aromatic amine, say for example this one, primary aromatic amine known as aniline, if this aniline is treated with NaNO2, sodium nitrite, and HX at a temperature of, or we can simply say HNO2HX, HNO2HX at a temperature of 0 degree to 5 degrees Celsius. It will result in the formation of benzene diazonium salt. It will result in the formation of benzene diazonium salt, and this reaction is known as diazotization. We will discuss this reaction in detail when we study, say benzene diazonium salt. So this is diazotization reaction. So today you have to remember, whenever aromatic aniline reacts with this, it will result in the formation of benzene diazonium salt, and at a temperature of this, because if you increase temperature, this is not stable after 5 degrees Celsius. After that, now this benzene diazonium salt, have a look. This benzene diazonium salt, upon treatment with Cu2X2, say cuprous halide and HX, or CuXHX, it will result in the formation of haloarene. And here halogen is either Cl or Br, and it is that halogen which is basically present in this copper. It is that halogen. Similarly, if you use Cu in presence of HX, this HX here can be Cl or Br. So the product over here will be that this bond will be broken, N2 will be lost, nitrogen gas will be evolved, and here it will be X. That means if X is Cl or Br, that means this can be either chlorobenzene or bromobenzene. Similarly, this can be chlorobenzene or bromobenzene. This reaction is known as Sandmeyer's reaction. This is known as Sandmeyer's reaction. And this reaction is known as modified Sandmeyer reaction, known as Guttermann's reaction. Guttermann's reaction. Now, if you are having this benzene diazonium salt, say for example, benzene diazonium chloride or benzene diazonium halide, if you treat this with aqueous potassium iodide and warm, it will replace this N2 and iodobenzene will be formed, and N2 will be, say the side product. Similarly, if we treat this with tetrafluoroboric acid, this negative part will be replaced, so it will result in the formation of benzene diazonium tetrafluoroborate. Now, if you heat this, this will be lost, and then N2 will be lost, and among a BF4 minus, F minus will attack, and it will result in the formation of fluorobenzene. So this reaction is known as Bals-Schimmann reaction. So during Bals-Schimmann reaction, benzene diazonium tetrafluoroborate or benzene diazonium salt forms fluorobenzene. During what we call Sandmeyer's reaction, chlorobenzene or bromobenzene will be formed from benzene diazonium salt by treating benzene diazonium salt with cuprous halide and HX, and during Guttermann reaction, chlorobenzene or bromobenzene will be obtained by treating benzene diazonium salt with copper and HX. After that, we are having chemical reactions of haloalkanes. Say for example, we are having few nucleophilic substitution reactions, as we have already discussed SN1 and SN2. Now, there are few examples of SN1 and SN2. Say for example, we are having alkyl halide. Suppose we are having alkyl halide, and to this alkyl halide, few reactions are there. Say for example, we are having reaction like this. Suppose we are having reaction with H2O. Remember, it will be an SN1 reaction. So first you have to form carbocation, and after that OH will be attached to that. So this will be the product. Similarly, if you use NaOH, then this will be a, so I will not write down SN2. So that reaction which will be SN1, I will write down SN1, other reactions will be SN2. So here it will be simply ROH and plus NaX. So this is NaOH, Na positive, OH minus, aqueous NaOH. After that, if I write aqueous KOH, once again SN2 reaction, and the product will be ROH plus KX. If I write AgOH, moist silver oxide or silver hydroxide, so at that time, once again, it will be ROH plus AgX. So these reactions are SN2 reactions. Similarly, if I write down what we call RONA, to differentiate this R from this R, so this is RO having negative charge, Na having positive charge, negative, positive, negative, positive, negative, positive. So this is once again SN2 reaction, so it will result in the formation of ROR prime plus NaX. That means ether will be formed here. Similarly, if you write sodium phenoxide, it's positive, negative, so negative part will attack this, X will be removed, so it will be ROPH, once again an ether. And this type of reaction is known as Williamson's synthesis. Williamson's synthesis. What is Williamson's synthesis? Remember, reaction of alkyl halide with alkoxide or phenoxide resulting in the formation of ether. But we have to study this Williamson synthesis in detail in chapter ethers. Now, after that, if you write NaSH, sodium hydrosulfide, it is positive, negative, then it will, negative part will attack as nucleophile and X will leave. So it will result in the formation of RH, that means thioalcohol and NaX. Similarly, if you write NaSR, this is sodium mercaptide, sodium mercaptide. Now, negative part, nucleophile will attack, X will leave. So what will be the product? RSR prime and NaX. After that, if you write NaN3, sodium azide, Na positive, N3 negative. So it will result in the formation of alkyl azide plus NaX. If you write R prime C triple bond C having a negative charge, so sodium alkanide. So this negative part will attack to R and X will leave. So it will result in the formation of R prime C triple bond C and this R. After that, NaX. If you write another reaction like R prime C double bond O OAG, silver salt of carboxylic acid, negative and positive. This negative will attack over this, so this will become R prime C double bond O and this R. That means ester will be formed. Ester will be formed plus AgX. Similarly, you can have other reactions as well. Say you are having, for example, you are having another reaction like R and M positive. M is metal over here. So it can be RMgX, it can be what we call R2CuLi, it can be R2Zn, I mean say Frankland's reagent, I mean say Gilman's reagent. So it can be anything. So this R minus, this R, this is having R dash. So let me write down over here. Oh. Chemical reactions of alkanes. So these are the chemical reactions of alkanes. So R minus will attack. This is R having a negative charge. This will attack. So it will result in the formation of alkane, and another will be MX, metal will react with this X. After that, if you are having hydride, say for example lithium aluminum hydride, sodium borohydride, lithium aluminum hydride, that can also attack. So after that, if you are having KCN, remember K positive CN minus, but CN minus is an ambidentate nucleophile. What is meant by ambidentate nucleophile? Different donor sites are there. So C will attack and it will result in the formation of RCN, or N will attack, it will result in the formation of RNC with a positive charge on N, negative charge on A, this C. And what we call KX will be lost, but this is major product. So this is an ionic compound, K positive CN minus. But if you write down AgCN, it's a covalent compound. That's why only nitrogen is the donor site. So it will attack and it will result in the formation of RNC, alkyl isocyanide plus AgX. Here it will be KX, side product will be KX. After that, so this is a covalent compound, that's an ionic compound. After that, if you write down KNO2, it is actually K positive ON double bond O. So it is having like this. So this is what we call an ionic compound. O minus can attack, N can also attack. So it will result in the formation of RONO, that means alkyl nitrite, as well as RN double bond O, and O having negative charge and a positive charge. Nitroalkane, alkyl nitrite. But O minus is stronger nucleophile, that's why this will be the major product. But if you write down the reaction with AgCN, sorry, AgNO2, that means AgONO. Here it is nitrogen which is more stronger nucleophile. That is why it will result in the formation of major product like this. This will be the major product and this will be the minor product. If another reaction takes place, say for example with NH3, it will first form primary amine. But when primary amine further reacts with alkyl halide, it will result in the formation of secondary amine. When this secondary amine further reacts with alkyl halide, it will result in the formation of tertiary amine. Tertiary amine on treatment with alkyl halide results in the formation of quaternary ammonium salt. And this reaction in which, remember, reaction in which alkyl halide reacts with ammonia results in the formation of quaternary ammonium salt via primary amine, secondary amine and tertiary amine. This is known as Hoffman's ammonolysis. Hoffman's ammonolysis of alkyl halide. In nutshell, whatever is the nucleophile will attack this and X will replace. This is one that type of reaction, that means SN2R. In presence of reagent, first carbocation will form. After that, nucleophile will attack like water or this ammonia. So this is SN1 reaction. If primary amine is a nucleophile, this is also SN1 reaction. Secondary amine acting as a nucleophile is also SN1 reaction, and this is also what we call SN1 reaction. So these are SN1 reactions. This is SN1. All other reactions are SN2 reactions. So you have to look towards your reagent and you have to choose the nucleophile. If nucleophile is weaker, SN1 reaction takes place. If nucleophile is negatively charged, that means stronger, then SN2 reaction will take place. After that, elimination reactions we have already studied in hydrocarbons. Already done in hydrocarbons. After that, reaction with metal, it's already done once again in hydrocarbons. So to understand haloalkane haloarene chapter, hydrocarbon is very, very important. Now reduction reactions already done in hydrocarbons. So go through hydrocarbon so that you can understand haloalkane haloarene more easily. Now have a look. That nucleophilic substitution reactions do not take place when there are haloarenes. Haloarenes generally do not show nucleophilic substitution reactions under normal conditions. First reason is resonance effect. Have a look. We know haloarenes, CX bond is difficult to break. In case of haloarene, CX bond is difficult to break because this bond is strong due to partial double bond character as a result of resonance. So it is resonance due to which this bond is strong and this bond cannot be broken. If this bond cannot be broken, we cannot do nucleophilic substitution reaction of haloarene. After that, second is difference in hybridization. Have a look. If you are having haloarene, hybridization of this carbon to which halogen is attached is sp2, and if you are having alkyl halide or haloalkane, its hybridization is sp3, which means its S character is 25% and its S character is 33.33%, and we know bond strength is directly proportional to percentage of S. So can I say here bond percentage is more, so this bond is stronger. As this bond is stronger, it is difficult to cleave. This is not stronger bond, that's why it can be easily cleaved. Or this bond is stronger, so this will be shorter bond. This will be a longer bond. Longer bond can be easily cleaved, so nucleophilic substitution can be done over here. But in this case, normal conditions, nucleophilic substitution is not possible. After that, instability of what we call phenyl carbocation. Say for example, haloarene is self-ionized. Say for example, this is broken. It will result in the formation of a phenyl cation, and this phenyl cation cannot show resonance because it is present in that orbital which cannot overlap with p orbitals. So there is no resonance stabilization. Second, this positive charge is present on more electronegative carbon. Positive charge and more electronegative carbon is unstable. So this is unstable. That's why this cannot be formed, or we cannot break CX bond, or we cannot form carbocation. After that, another is, we know this is what we call haloarene. And we know in case of haloarene, this aromatic ring is basically showing overlap like this. These orbitals will overlap and these lower orbitals will overlap. That means here will be pi electron cloud above and below the plane. When nucleophile wants to attack, nucleophile is already electron rich, so there will be electron repulsion. As this is already electron rich, this is electron rich, there will be electron repulsion, though there will be no what we call nucleophilic substitution at all. After that, replacement by hydroxyl group. That means if we want to do nucleophilic substitution reactions of haloarene, say for example Dow's process, I mean to say, if we want electrophilic substitution of chlorobenzene, haloarene, what we have to do? Simply, we have to take this reaction, say for example NaOH, we have to take this reaction, nucleophilic substitution reaction, but under drastic conditions, 623 Kelvin and 300 atmospheric pressure, and followed by acidification. Then this Cl will be replaced, and there will become the nucleophile will come to this place, and the product will be phenol. So this is known as Dow's process. But remember, this reaction is nucleophilic substitution reaction, but this nucleophilic substitution reaction takes place through a mechanism known as benzyne mechanism, or this is known as basically elimination addition reaction. Have a look. First of all, nucleophile will abstract hydrogen from ortho position with respect to the leaving group. It will result in the formation of a carbanion, then it will form a bond and Cl will leave. That means benzyne will be first of all formed. Benzyne intermediate is formed. But we know this another bond is basically due to formation of sp2 hybrid orbital overlap. And we know pi bonds are generally formed by overlap of unhybrid orbitals. But here hybrid orbitals overlap. That means it is an unusual overlap. This bond is not stable. Because of this pi bond, it becomes reactive. Now OH will attack either this position. If it attacks this position, so OH will go here, pi electrons will go there, so it will become negative and Na positive will be there. Or this will attack this and this pi bond will go there. So these two will be formed. After that, now water, it will abstract this negative, or this negative charge will abstract hydrogen from water. So it becomes H, also it becomes H. So either this or this. That means phenol will be formed. But phenol will act as acid because it's having acidic hydrogen. And in basic medium, phenol is converted to what we call its sodium salt. That means phenol cannot be recovered here, as this base will convert it into salt. That's why we add dilute HCl so that phenol can be formed, because when we add dilute HCl, this HCl first forms phenol, and second it will simply dilute, it will simply neutralize all the base there so that phenol can be recovered. But have a look. Cl was attached to this position. OH can be replaced, that Cl can be replaced by OH at the same position, or OH will come to that position which is adjacent to the position attached to the leaving group. This is known as normal nucleophilic substitution product, but this product is known as Chinese substitution product. Which is known as Chinese substitution product? Remember, that product in which nucleophile goes to that position which is adjacent to the position position of leaving group. So this is the position of leaving group. This is the position adjacent to the leaving group. Nucleophile goes to that. But if nucleophile goes to that position to which leaving group was attached, this is known as normal nucleophilic substitution. In short, this Dow's process takes place through benzyne mechanism. First, H and Cl will be lost. That means elimination takes place. After that, here H and OH will be added. That means addition. So this is elimination addition mechanism or benzyne mechanism. And second thing, you have to remember that phenol is obtained from chlorobenzene during Dow's process, but either through normal substitution or through Cinay substitution. After that, have a look. Now, if I simply add electron withdrawing group at para position, rate of reaction will be increased. Rate of reaction will be increased. That is why we can do this reaction at lower temperature as well. We can do this reaction as lower temperature as well. That means first more drastic conditions were needed. Now that type of drastic conditions are not needed now, as reaction will be faster due to electron withdrawing group at para position. Similarly, if we add electron withdrawing groups at ortho and para position, with respect to leaving group, then what will happen? Reaction rate will be more. That's why we can do the same reaction at a lower temperature than this one as well. So the product will be Cl will be lost, Cl will be lost, Cl will be lost, and instead of Cl, OH will be there, and this will become NO2 and NO2. And if if this NO2 is attached to both the ortho positions and para positions, that means rate will be very, very fast now due to presence of electron withdrawing groups. That's why reaction can take place by using weaker nucleophile instead of this, and that too by warming only. That means product of this reaction will become like this. This is known as 2, 4 and 6 trinitrophenol, commonly known as picric acid. So I mean to say, rate of this reaction is increased by simply introducing electron withdrawing groups at ortho and para positions, but not at meta position. Why is it so? Why not at meta position? Have a look. Because if you add ortho of what we call nitro groups at ortho and para position, negative charge formed will be in direct contact with NO2, or negative charge formed here. Have a look. Negative charge will be here resonance stabilized if it is at para position. Similarly, negative charge will be stabilized due to NO2 group due to resonance. But here negative charge is not present at carbon which is directly attached to NO2. Have a look. Neither negative charge is present at ortho, not at meta, at para, not at meta. So that means ortho and para position in a nitro group, electron withdrawing group at ortho and para position can stabilize negative charge more as compared to meta. That's why rate will be faster in case of ortho and para, and among ortho and para, ortho will be more faster than para, and after that it will be meta, or this will be a slow reaction. And remember, these are different resonating structures, and this is the hybrid, and this hybrid is known as Meson-Hammer complex. Meson-Hammer complex. And this Meson-Hammer complex is formed in rate determining step. That's why reaction, remember, rate of this reaction is directly proportional to stability of Meson-Hammer complex. Meson-Hammer complex. So that reaction, that substrate which forms more stable Meson-Hammer complex, will show this reaction faster. That means ortho will show this reaction more faster, as it will stabilize this by resonance as well as inductive effect, and this will stabilize negative charge by resonance. and then this is in close proximity. That's why it will simply increase deficiency over here more as compared to this NO2 here. So first ortho, then para, and then meta. Now tell me, if I replace this Cl by Br, I and F, so if we are having 4 options, one is F, another Cl, another Br, another I, then what will happen? Which will be the rate of reaction will be faster in F, then Cl, then Br, then I. Why? Because this F, Cl, Br, I will be lost. That means leaving group will go, but in rate independent step. So it's not depending upon leaving ability, but it depends upon stability of this Meson-Hammer complex. F will stabilize negative charge more due to more minus I. After that Cl, after that Br, after that I. I hope this is clear. Now, after that, it's electrophilic substitution reactions. Have a look. If you are having haloarene, have a look. Now, this haloarene will donate electron due to resonance and increase electron density at ortho and para position. That means electrophilic substitution reactions will take place at ortho and para position. Suppose you are having first chlorination. Say for example, if I use chlorine over here, because X can be chlorine or bromine. Generally we use chlorine or bromine. So if I use Cl2 in presence of anhydrous AlCl3, remember these will form Cl2, chloronium ion, as an electrophile. So chloronium ion goes to either ortho or para position. So the product of this reaction will be this one or para, this one plus HCl. So this will be major because of lesser repulsion. Their repulsion will be more, so this will be minor. Though this is halogenation. So in case of halogenation, halonium ion will act as a what we call electrophile. After that, we will do nitration. Nitration generally takes place by using concentrated nitric acid and concentrated sulfuric acid. In this reaction, concentrated sulfuric acid will act as an acid and HNO3 will act as a base, and this H2SO4 will helps in generation of electrophile, and electrophile of this reaction is nitronium ion. So this nitronium ion will go either to ortho or para position, because in case of chlorobenzene, in case of haloarene, electron density will be more at ortho and para position. So electrophile will go to ortho and para position. So this reaction is known as nitration because we have introduced nitro group, in this benzene ring. Here we have introduced halogen, so halogenation, this is nitration. After that, sulfonation. Say for example, concentrated sulfuric acid is there. So here electrophile is neutral SO3. First it will accept electrons from this benzene ring and becomes SO3 minus, and finally it will abstract hydrogen from ortho and becomes SO3H. Similarly, first it will accept electrons from para position and becomes SO3 minus, then it will abstract hydrogen from para position and become SO3H. In nutshell, we have introduced SO3H. SO3H is known as sulfonic acid. Introduction of sulfonic acid group is known as sulfonation. So this is major product and this is also major product. After that, if we use alkyl chloride in presence of anhydrous AlCl3, electrophile of this reaction is R positive. So as it is alkyl carbocation, so rearrange if possible. First you have to rearrange if rearrangement takes place. After that, the most stable carbocation, alkyl carbocation, goes to either ortho or para. So the product will be simply introduction of alkyl group at ortho or para. But first you have to look whether carbocation undergoes rearrangement or not. If carbocation undergoes rearrangement, you have to rearrange that. So this will be the major, because at ortho repulsion will be more. After that, its another reaction is simply a reaction of acid chloride in presence of AlCl3. Remember here electrophile will be Rc positive double bond O. but there will be no rearrangement as this acylium ion can undergo what we call back bonding. This is back bonding stabilized carbocation. Hence, there will be no rearrangement. So, this carbocation will either go to ortho or to para position. Now, have a look. It will go to para position or it will go to ortho position. But the major product will be always ortho. Major product will be always para product because repulsion will be less. So, this will be major. And at the very same time, HCl will be the side product. So, this is halogenation or chlorination. This is nitration, introduction of nitro group. This is sulfonation, introduction of sulfonic acid group. This is alkylation, introduction of alkyl group. This is acylation because of introduction of acyl group. So, this is Friedel-Crafts acylation, Friedel-Crafts alkylation. So, these two reactions are Friedel-Crafts reaction. So, these two reactions are Friedel-Crafts reaction. You can write down over here. These are Friedel-Crafts reactions. So, Friedel-Crafts reactions are of two types. Friedel-Crafts alkylation, this one, and Friedel-Crafts acylation, this one. So, I hope this is clear to you. After that, reaction with metal. Have a look. If you are having aryl halide and you treat it with sodium, for example, like this. Whenever you have CX bond, I have told you that if you are having CX bond, I have told you that in hydrocarbons in Wurtz reaction, whenever you have CX bond, you just cleave that bond and it will result in the formation of this NaX, but it will result in the formation of a radical. CX bond and sodium is there, so radical formation is there. Similarly, radical formation is there. This is the trick. So, this radical and this radical will combine and it will result in the formation of biphenyl. So, it will result in the formation of biphenyl when reaction takes place in presence of dry ether. So, this is similar to Wurtz reaction, but only difference is that Wurtz reaction was reaction of alkyl halide with sodium. This is a reaction of aryl halide with sodium. So, this is known as Fittig reaction. This is known as Fittig reaction. This is one. Another is Wurtz-Fittig reaction. Wurtz-Fittig reaction. That means combination of Wurtz and Fittig reaction. It's simply a reaction of aryl halide and alkyl halide with sodium in presence of dry ether. So, it will result in the formation of NaX like this, and it will result in the formation of R radical, it will result in the formation of phenyl radical. Now, two different radicals are there. So, there are possibilities. R will react with R, that means alkane can be formed. This benzene phenyl radical can form, react with phenyl radical, that means biphenyl can form, or these different radicals will react and they will result in the formation of alkyl benzene. So, I have written only this one because this is the major product. So, this will form. So, a reaction of aryl halide with sodium resulting in the formation of biphenyl in presence of dry ether is known as Fittig reaction, and reaction of alkyl halide with aryl halide in presence of sodium and dry ether resulting in the formation of alkyl benzene is known as Wurtz-Fittig reaction. Now, after that, we are having few questions over here. Have a look. Now, whenever thionyl chloride is there and you are having OH, you have to just replace OH by Cl. This is very, very simple reaction. Now, whenever you are having what we call this, say alkyl benzene, or you are having side chain attached to benzene, and then bromination takes place in presence of heat or light, this is known as benzylic bromination. That means you have to remove benzylic hydrogen by halogen, and halogen here is bromine, so this will be the product. Here it is simply Markovnikov's addition. So, across double bond, negative part of addendum, that means negative part goes to that carbon-carbon double bond which is having lesser number of hydrogen. So I will go to here and hydrogen will go here. So here already one hydrogen was there. So now two hydrogens will be there. Now this is Finkelstein reaction. Replace Br by I. SN2 reaction, Finkelstein reaction. Okay. After that, simple reaction. It is, have a look. It's not addition of halogen in presence of dark. If it is addition of halogen in presence of dark, you have to remove pi bond and add bromine and bromine. This is addition of halogen in presence of heat or light. That means it is free radical या allylic halogenation. So you have to remove H, form radical, allyl radical, and after that you have to check all the resonating structures of those allyl radicals, and after that you have to add Br radical. So this is the product of this reaction. Now here simple, it is simple electrophilic addition reaction, and negative part of addendum goes to that which is having lesser number of hydrogens. So this will be the product. Here Hi, once again this is positive negative, that means we will form electrophilic addition reaction product, that means Markovnikov's product. I will go here and H will go here. But here it is addition of HBr in presence of peroxide, that means it is anti-Markovnikov's product. That means you have to form like this. You have to break carbon-carbon double bond, and to this you have to add hydrogen, and to this you have to add bromine. That means negative part here goes to that carbon-carbon double bond which is having more number of hydrogens. Simple questions were there. Next, compare reactivity. Now have a look. This is 1 degree, this is 2 degree chloride, because this is attached to 1 degree carbon, this is attached to 2 degree carbon. We know 1 degree is showing more rate of SN2 as compared to 2. So the answer of this reaction is 1 greater than 2. Now good leaving group as compared to this, so 1 greater than 2. After that, this is 1 degree, this is 2 degree, once again 1 greater than 2. This is 2 degree, this is 3 degree, so 2 greater than 3. Because whenever at alpha, only alkyl groups are on one side, here it's on two sides, that means secondary. So this is secondary, two sides alkyl group, and here three sides alkyl group. That means more alkyl groups are present over here. So more the number of alkyl groups at alpha position, lesser will be the rate of SN2. Now this is alpha, this is beta, this is gamma and delta. Similarly, this is alpha, this is beta. Now have a look. Nucleophile has to attack alpha position, but at beta, that means adjacent to alpha position, there is crowding. So nucleophile feel hindrance here as compared to this. So 1 greater than 2 will be the answer. After that, okay, have a look. Whenever magnesium and CBr bond, CX bond is there, remember forever, CX bond is broken and magnesium is incorporated between C and halogen. That means this is the A. This is the A. After that, this is negative part, this is negative part, and this is positive part. This negative part will abstract hydrogen from acid, because this is, this is Grignard's reagent. Grignard reagent will act as a base. So this will abstract hydrogen. It will abstract hydrogen from acid, and it will result in the formation of cyclohexane. So here will be hydrogen, and MgBrOH will be the side product. Now, once again, this will become RMgBr. This is RMgBr. Now the question is, this R is having negative charge, Mg positive charge. This will abstract proton here, but proton is in the form of D positive. So it will result in the formation of Rd. So this is D. So what will be this R? What is this R? R is CH3, CH, CH3. That means this is CH3, CH, CH3, and then MgBr. So C is this. So we have to find out A, B, C. Now we will find out D. Whenever it reacts with this, it results in the formation of R prime MgX. After that, this is having negative charge, this is having positive charge. So this will become RH. Now the question is, it undergoes Wurtz reaction. Wurtz reaction product is this. So this is CH3, CCH3, CH3, monomer of this. So this is the alkyl halide. So if R prime is this, that means this is CH3C, CH3, CH3, MgX. So this is our D, this is our D, then E will become CH3, C, CH3, CH3, this is R prime, then H. So this is E. So this is A, this is B, this is C, this is D, this is E, and we have to find R and R prime. So this is R prime is, say R prime is C, CH3, CH tertiary butyl, and R is isopropyl. So everything is clear. Now, after that, okay, aqueous, this is alcoholic potassium hydroxide, that means it's E2, alpha, beta. Remove hydrogen from beta and form double bond between alpha and beta. Now, this is once again phenyl magnesium bromide, because function, whenever CX bond is there and magnesium is there, magnesium should be between C and X bond. Aqueous, this is SN2. When it is aqueous KOH, SN2. Alcoholic KOH, it is E2. So the product will be like this. Cl will be replaced by OH. Sodium, okay, so this is what we call Wurtz reaction. So break this, form a radical and combine this with the similar radical. So this is the product of this reaction. KCN, K positive, CN minus. That means it's an ambidentate nucleophile. This will be the major product. This will be the major product. Side product, I have not shown side products. I have shown only the major products over here. Now, NAI. So this is in acetone. This is Finkelstein reaction. So it will simply result in the formation of alkyl iodide. This is KOH and alcoholic. So alcoholic KOH. So this is alpha, this is beta, this is beta, this is beta. We have to simply remove hydrogen from beta and form double bond between alpha and beta. So this is E2 reaction. So this is E2. This is E2 reaction. This is SN2 reaction. This is SN2 reaction. This is Wurtz reaction. This is E2 reaction. Okay. Now after that, this is SN2 reaction. So remove Br and attach OH there, CH2, CH3. After that, this is negative, positive. So this negative will attack over this and Cl will be lost. This is SN2 reaction and it will result in the formation of ether, C6H5, O, CH2, CH3. This is known as Williamson's ether synthesis. Now, whenever OH and SOCl2 is there, remove OH and add remove OH and add Cl2. Sorry, remove OH and add Cl. Side products will be HCl and SO2. Now, here you have to add HBr, but according to anti-Markovnikov's rule, because this is peroxide, so anti-Markovnikov's rule. So this is Markovnikov's product. This is anti-Markovnikov's product. So product over here will be CH3CH2, single bond CH, single bond CH2. Here it will be Br. Here it will be H. But in this case, CH3CH2, CH, Br, and after that CH2 and H. Next, here it's sodium ethoxide, strong base. What will it do? Say strong base. This is alpha, this is beta, this is beta, this is beta. Two types of products will be formed. Either product will be formed from this beta, base will abstract hydrogen, or from this beta, base will abstract hydrogen. This and this, one and the same. These two are same beta hydrogens. So I have not write down that this becomes C2H5OH or Br minus will be the side product. I have not written that. So this is Hoffman product. This is major. This is, say Sedze product and this will be major. This is Sedze product and this will be major. Okay. Now similarly, this is alpha, this is beta, this is beta. These betas are identical and this beta is different. So there are two types of products, CH2, double bond C, CH3, then CH2, CH3, because you have to remove beta hydrogen and form double bond between alpha and beta. Another product will be CH3, C, CH3, double bond CH, single bond CH3. So this is Sedze product and hence major product. You have to find out major product and this is Hoffman, say minor product. Why Hoffman? Because from a rich if we abstract hydrogen from rich beta position, which is rich with respect to hydrogen, it will form Hoffman. And from that, if we abstract hydrogen from that beta position, which is not rich, which is poor, that will result in the formation of said Z product. Now, this is alpha, this is beta, this is beta, this is beta. This beta does not have any what we call hydrogen, so either from this or from this, so the product will be CH3, C, CH3, CH3, single bond C, double bond CH2, single bond CH2, single bond CH3. This will be Hoffman, and another product will be CH3, C, CH3, CH3, C, CH3, double bond CH, single bond CH3. This is this product will be said Z product and hence major product. So this is all for today. So this is end of this chapter, and thank you very much to all of you for having such a patience. But you have seen that this chapter depends mainly on hydrocarbon, and that is why I want you all guys that you will study hydrocarbons very, very, very nicely. And after I end this, live session, after ending this live stream, I want you all guys at the end to comment in the comment section, but not here live during live chat. I want, after completion of this, I want message or what we call comment from each and every one among you that how much you liked today's session, and I hope everyone has, understood this whole chapter. But you have seen that this chapter is mainly dependent on hydrocarbon. So I request each and every one go through that hydrocarbon first, and after that go through this chapter once again, so that every concept will be cleared. So good night, take care, and thank you all.